hello check, hello check, check, hello check, hello check, hello check. साउंड कर दो।
Sorry. Okay, good morning. Let's start the first session today, the early universe, quantum mechanics of inflation. So the first speaker is Diptymon Ghosh from Indian Institute of Science Education and Research, Pune. And I let the speaker explain the title. So 70 minutes plus 3 minutes discussions.
Okay, so thanks for the invitation. So this is what I'm going to tell you about. I'm going to tell you about how effective field theories work in inflationary setting, which has a time dependent background, and how things are peculiar or at least different from our intuitions we gain from flat space. But before I start, let me first acknowledge my institution, in particular my colleagues. 2 of them are here for providing a very supportive environment. Then the funding agencies where I get money from, and finally all my PhD students and master students and collaborators, unfortunately I don't have their photographs, who have taught me everything I know about this subject, which I didn't know anything about 3 to 4 years ago. Okay. I have had equally good other master students, but they don't appear here because they are not directly relevant for this talk. Okay, so let's start with what we know about effective field theories. Effective field theories are very important because, as you all know, nature comes with many scales, but still we can make scientific progress because we can talk about one scale at a time and kind of forget about all the other scales, and that doesn't really mean we forget about all the other scales. That means that our lack of knowledge about the other scales can be taken into account by a finite number of coarse-grained parameters which we can measure experimentally. Like for hydrogen atom problem, we can just talk about proton mass, which is a complicated object, which is made of lot of things, lot of microscopic things. But as long as we know the proton mass from low energy experiments, we can compute hydrogen atom spectra. Many examples of effective field theories, starting from our undergrad education, multipole expansion, then Fermi theory, and then also hydrodynamics. Almost in all areas of physics, there are a lot of examples of effective field theories. In the context of inflationary cosmology, you might know about the effective field theory of inflation. In the context of large scale structure also, you know that there is a hydrodynamic description of large scale structure which goes by the name of effective theory of large scale structure. So effective field theories are everywhere, and in fact we can do physics because effective field theory works. Now let's take an example. Let's take the example of a flat space effective field theory, where we want to describe the scattering of a light scalar field small phi, the red phi here, mediated by a heavy scalar field this phi, which is blue here. Now this would be the standard diagram. This is a tree level diagram, even high schoolers can compute, just multiply couplings, propagator and coupling. So that's what we get. Now if you are interested in scattering at very low energies, what you would do, you would do an expansion of this quantity in powers of s by m phi square. This is small, so this is like 1 by 1 minus x, where x is small. So this series is convergent. So that's very important, and this is what you get. Now for each n, you can understand this factor, the scattering amplitude coming from an operator like this. So you have 4 phi's because you are doing phi phi to phi phi scattering, and then there are 2 derivatives to the power n. So that's what you do if you write down an effective field theory in flat space. And the important thing is that in the regime where this quantity is small, this series is convergent, and higher derivative terms contribute less and less. So that's why you can reliably truncate this and compute the scattering amplitude, and you can expect this to be an exact extremely good approximation to the full answer. So that's how it works at tree level. At loop level also you have a similar story. Of course, implementing EFT in loop level is slightly more complicated, but it's done. It's a textbook material for flat space QFT. Now let's try to do the same thing in cosmology. And in cosmology we don't have a natural way to define S metrics. Even if there were some definition of S metrics, it would not be very useful, because in cosmology, as far as we know, the universe did not start from a state prepared by experimentalists. So we can't really prepare the universe in a state, see the time evolution, and then measure the state at a later time. So we can't talk about transition amplitudes. They are of questionable utility in cosmology. So we talk about correlators, in particular equal time correlators at the end of inflation. then you run some machinery to translate it into equal time correlation functions on the CMB sky or for large scale structure. Now, so these are called in correlators, and this is what they are. They are exactly what we do in quantum mechanics. There is nothing very strange or new. You have a state which is the state of the universe at the end of inflation. You insert some operator and you just compute the expectation value of that operator. This is a more detailed formula of the in correlator, and this is a diagrammatic representation where you start from some initial state, you go evolve it to go to end of inflation, then you compute and again come back because you can't define the out state unlike what you do in flat space QFT. Okay, so this is the object of interest. This is not matrix which we had in the last slide. This we want to compute, and then now let's again do a similar exercise here. Here you have again a light field mediated by a heavy field. So this would be the diagram where the propagator would look like this. And now again, if you series expand this, you will get this. And for each n, if you compute the 4-point wave function, which is slightly different from a correlator, but which is related to the correlator, I haven't exactly defined this, but it's not so important. What you get is this. Now you would notice that you have a factorial growth of this object as a function of n, which is very different than what we actually see in flat space QFT. So this means that if you had an operator with an extremely large number of derivatives, using flat space intuition you would think that that contribution is extremely small. But because of the factorial growth, that contribution could be extremely large. So the standard intuitions of flat space QFT actually fails here. Now this is not unexpected. This is not unexpected once we realize that this propagator is can be written as k physical. So this k is in momentum space, this k is k co-moving. But if you write this as k physical, then because of blue shift in the past, this k physical at some point becomes larger than m phi. So this object becomes larger than 1, and then of course if you expand, this is not going to converge. So and this is happening exactly because of the time dependence of the background, because in a more technical language, in the in correlator you have to do these time integrals from very early time to the end of inflation, and in the time integral at some point, this 1 by 1 minus say x, this x becomes more than 1, so if you do an expansion it doesn't converge. So this is not unexpected, but this is the peculiar nature of effective field theories in the context of inflation, and that's why is absolutely unclear how to even think about effective field theory in the cosmology context. Okay, so this is the first peculiarity I wanted to point out. The next one is not a peculiarity, but is a feature of effective field theories for inflation, is about how unitarity works in the context of inflation. Now, for flat space, you know that unitarity plays a very important role. Those who have worked on particle physics know that even for Higgs discovery it was very important. I mean, we kind of knew that Higgs has to be light in order for the theory, which is the standard model of particle physics, to be unitary beyond a TeV scale. This unitarity also gives very quantitative predictions called cutting rules or optical theorems in flat space QFT, and it also tells you where to stop. In physics, like in life, is important to know where to stop, and unitarity gives us a tool to understand where to stop. It tells you that this theory, let's say in standard model of particle physics, without Higgs would only work below a TeV, not beyond. So you have to stop at TeV to get reliable predictions. Now, so that's why this is very important, but in cosmology it's very different. is very different, because cosmology, if you think about it, is a science without time. Because what we measure are some equal time correlation functions on the CMB sky. So they are completely spatial patterns, completely spatial correlation functions. We measure them and then we infer the existence of time, and through some self-consistent set of rules starting from some initial state, we compute the time evolution and get again the correlation at the equal time surface, and then we measure and match them with experiments. So we don't really see the time evolution, very different from particle physics, where we can start a state, see the time evolution and measure it. In cosmology we can never see the time evolution. So how do we talk about unitarity in the cosmology context, and what would be the consequences or constraints coming from unitarity? Now there have been partial progress in answering these questions. In particular for Barnes-Davis like initial states, a group at Cambridge have made some progress. We have also extended and understood what happens in states which are not Barnes-Davis but some excited states. Now just to give you a feeling of what kind of constraints we get from unitary time evolution, if you look at the wave function again coefficients for contact diagrams, for example, any endpoint, it does not have to be 3 point, for any endpoint contact diagrams, you actually see relations like this. This will translate into a slightly more non-trivial constraints on the correlators. In terms of wave function coefficient, these constraints are simpler. If you see exchange diagrams like this, you will actually see a factorization. So a 4-point exchange diagram can be written as a product of 3 point times 2-point function. So this is also very similar to what happens in qualitatively similar to what happens in flat space, where you have a factorization of higher point amplitudes in terms of lower point amplitudes. So you get a qualitatively similar feature, but it's very premature compared to what we know in flat space, because in flat space unitarity is also understood in terms of insertion of complete set of states in some transition amplitude. So you have a non-perturbative understanding of unitarity in what is called optical theorem there, which is a non-perturbative statement in flat space QFT, but here this is completely diagrammatic. We don't have an understanding in terms of complete state of states, so we don't have a non-perturbative full understanding of how unitarity works here. So this is not yet as complete as S-matrix unitarity for flat space, but at least there is some progress. How much time do I have? 3-4 minutes, okay. The last point I wanted to make is the constraints from causality in the context of inflation or cosmology in general. Now again in flat space, you know that causality, which is just the statement that if you consider any theory and then consider fluctuations, these fluctuations should not go outside the light cone. Now this gives very non-trivial constraints on the space of theories you can write down in flat space QFT. For example, if you take this simple Lagrangian, which is a Lagrangian of Goldstone boson having a quartic interaction, is naively looks completely fine with any sign of the coefficients k is completely Lorentz invariant and so on. But causality in the flat space context tells us that this kappa must be greater than 0. For negative kappa, the theory will break causality. So the theory will allow superluminal propagation of signal, which you can't naively you don't naively expect from this Lagrangian. In the same way, in a theory of photons, this is called a Euler-Heisenberg action, because Euler and Heisenberg wanted to understand photon-photon scattering, which doesn't happen in Maxwell's theory. Maxwell's theory is completely free, and wanted to understand whether there are they wrote down this theory, but they with kappas as completely arbitrary constant to be measured from experiments. But again, causality tells us that these coefficients all have to be positive, otherwise the theory will break causality. So these are constraints on parameters of the theory coming from causality. In quantum mechanics, which is just the statement that if you take any operators of chain of operators, their commutator must vanish outside the light cone. Now, the question is whether we have similar constraints for the coefficients of an effective theory which we write for inflation. Now, these constraints, for these constraints, a necessary precursor is the analyticity of the amplitude. This is very similar to Kramer's chronic relation, which we learned in optics. The causality tells you that the response function must have some analytic properties. So, here also the S matrix has some analytic properties. So, we have to know that what analytic properties these wave function coefficients or correlators have for inflation. In flat space, we get all our intuitions by these analytic properties. We know that there are these poles and branch cards. Poles corresponds to physical particles being exchanged, branch cards corresponds to some multi-particle thresholds and so on. So, these analytic properties are very important. There have been very little progress again in this direction. Say for example, for flat space wave functions, people have understood that all the non-analyticities are on the negative real axis. For correlators, we have tried at least at the one loop level. We have also seen a similar structure. All the non-analyticities, poles and branch cards, they are on the negative real axis. You will probably see a little bit more about it by the talk by Suprita on Friday, which is tomorrow. Yeah, tomorrow. And here it's very difficult to make progress because loops are extremely difficult. Yeah, I'm almost done. So, loops are extremely difficult here. Just to give you a feeling about how difficult it is, the first loop was computed by Weinberg, simple loop, 2-point function for cosmology, and he did a mistake. This mistake was of course corrected for 2-point function again by Senatore and Zaldarriaga, and later on we extended it to 3-point function for bispectrum recently. But this is just to give you a feeling that a person like Weinberg, I am not talking about myself, talking about Steven Weinberg, who did a mistake and who had an absolute mastery in computing loops in flat space. Because in cosmology, even tree is complicated because of this complicated nested time integrals. So, loops are very difficult. Although we have some idea about analytic properties because of the lack of crossing symmetry and Lorentz invariance. In the inflationary background, we don't have Lorentz invariance. We still don't have a UV-IR dispersion relation and positivity, but people are making progress. In fact, this is exactly the reason why the significant part of theoretical cosmologists nowadays are trying to understand positivity bounds for non-relativistic theories which do not have Lorentz invariance. Okay, so I think I should stop. So, just to summarize, I think the application of effective field theory to cosmological or let us say de Sitter correlators reveals profound departures from flat space-time expectations. They are not super unexpected because of the time dependence of the background, but it just tells you that we have to really rethink about how EFT works in this context. For fast space QFT, there are textbooks. If you want to learn about EFT in the Cosmo context, there's not even single textbook which talks about it. It basically tells you the status of the subject and how much we understand. I think we are still, compared to what we know in flat space, we are still at the base of the mountain, and we really have to make a lot of progress to be even at a comparable stage of understanding which we have for flat space EFT. Thank you.
Thank you, Deep Mori, for a very nice talk. So maybe one or two. Okay.
Hi, Deepthi Mike. Just one remark and a couple of questions. The fact that you mentioned it, de Sitter is significantly different. So, I mean, flat space expectations are unlikely to hold true. Number one. Number two is that in real inflationary calculation, de Sitter approximation, particularly when you talk about scalar perturbations, is bad. So even the de Sitter symmetries are not going to help you. So you need to be careful. You need to actually calculate in slow roll inflation. And lastly, there is loops, I understand, are an issue, calculating them. But there are no conceptual issues, to my knowledge, in just calculating higher order correlations.
Loops
Loops are a challenge, I agree. The regularization and the renormalization remains to be understood, particularly in non-trivial situations. So in such a situation, the issues you're talking about effective field theory seems to be more an issue with effective field theory than ability to calculate using simple quantum field theory techniques.
Okay, so you are absolutely right. So one thing about de Sitter, I mentioned de Sitter because often is approximated by de Sitter, but almost everything I said is true about real inflationary background. And indeed, you are completely right that de Sitter is often not a good approximation for inflation. Say, for example, if you take the endpoint function of zeta, the curvature perturbation, in the pure de Sitter limit, they are all 0. This is just to I said de Sitter just as an approximation. So this is one thing. Now, and indeed, also your last point about higher point correlators, there is no problem in computing. If you write down and if you have a Lagrangian, you start from some initial state, you can compute. But now the question is, like in flat space, let's say that I'm given EFT of inflation. The EFT of inflation has some higher derivative operators suppressed by let's say some cutoff, often taken to be M-Planck, but doesn't have to be some lambda. Now the question is, I can compute it, but how do I know that the computation is producing the UV answer from where the EFT operators are coming reliably? Now these facts, so that's why I said this fact is not very clear unless we have an example where we know the UV and also the IR, we can match and see that they actually agree. This is the standard matching procedure for flat space EFT. Now here it seems that this matching procedure is not very clear how to do, because you may have some UV thing, but it doesn't really have a good IR description in the way we think about in flat space EFT. Because in flat space EFT, very high derivative operators we'll just ignore, we'll truncate and say that okay, all high derivative operators will not contribute.
Yeah,
but here
de Sitter or inflation, there is another scale involved.
There is another scale involved, but you see, this is Hubble by lambda, but then there is this factorial growth which doesn't allow you to reliably calculate unless you know the full UV theory. But given that you will never know the full UV theory, we would like to have a setup where we are insensitive completely to the UV. So that is a challenge in EFT. And also, if you even think about it, you see in flat space we have some low energies compared to some heavy scale, we kind of understand what EFT is. But in cosmology is very different, because if I start from some k, this k is large, or say the wavelength is large now, but in the past it was extremely small, so it was part of the UV theory in the past. So even physically, how to think about effective field theory in cosmology is not very clear. Of course, if you start from some initial condition, you can compute.
Okay, yeah, it's very interesting discussions, but I think we have to leave the discussion to the coffee time.
Can I ask?
Okay, very short question.
So it's a clarification question. So you made a comment about that we cannot see the time evolution in context of cosmology. So my this doubt is that we know the evolution of the scale factor and how the universe evolves. So what is exactly meant?
So you see, in the inflationary context, you see that we actually measure the spatial correlation functions at the end of inflation. Before what happened, we actually don't know anything about. We cannot directly access that time. This is exactly like what people do in what detectives do. You see, detectives, they actually say, oh, there's a big bullet in somebody's body and so on. They actually see, so these are all spatial patterns. So there's a bullet here, there's a person there and so on. From there, what do? They try to reconstruct the history, right? They don't see the history. Through some logic, they try to reconstruct, maybe this person shot this person, blah, blah, blah. But this is all a logical logical
Continuation.
evolution to the past, but which is in our head. We don't see it. Is very different in flat space where, or in condensed matter system, or any experiments we do. You prepare a state, you actually can evolve and see at any time what the state is doing. So this is very different in particle physics, or everything we do actually in practically in all experiments on Earth. But in cosmology, in particular in this case, you see we can't see the time evolution. We only see the end product, which is some spatial correlations.
Okay, I see.
Okay, let's thank the speaker again. The next speaker is Srinath from NITK. The next speaker is Srinath from NITK. He will be talking about Gaussian, yet non-Gaussian. Gaussian, yet Gaussian.
Good morning. First of all, I would like to thank Dheeraj and organizers for inviting me here. The goal of this talk is to describe our efforts in estimating primordial non-Gaussianity, imprints of primordial non-Gaussianity generated in loop quantum cosmology in the cosmic microwave background. This is a work which I did with my student Roshna. So loop quantum cosmology is an attempt to extend inflationary regime to the Planck era. So in this scenario, prior to inflation, there is a bounce. So the universe started in a contracting phase. There was a contracting phase before the bounce, and after the bounce, universe accelerates. So the background dynamics is governed by modified Friedmann equation. As you can see, the Friedmann equation has been modified with nonlinear terms in density, and there is a supremum density in the theory. If rho is equal to rho sub, A dot is 0, and if you compute A double dot at rho equal to rho sub, you will see that it is actually a minimum. And if you have a suitable potential, you can have bounce and then followed by inflation. So the background dynamics is illustrated here. So scale factor decreases to some value and then starts expanding again. At late times, you have an inflationary epoch. So there is a bounce followed by inflation. And energy density does not go to infinity as in GR. Energy density reaches a maximum value, which is rho sub. And this is the evolution of scalar field. So idea is to study evolution of perturbations in this background. So we will assume that perturbations are test fields living on this background. So we consider fluctuations to the scalar field, and we treat them as quantum fields. So we expand, we promote them to operators by expanding them using annihilation and creation operators in terms of the classical solutions. Phi k are the mode functions. So basically we are interested in quantifying this perturbation and to study what are the observables, to tie them to observables in the CMB. So we need to study correlation functions. So the correlation functions that we will study are 2-point functions, 3-point functions, and so on. So this is how you can define the correlation functions of, in this case, 2-point correlation functions of delta phi. And you can see that the 2-point correlation function, so basically this is how you define the power spectrum of 2-point correlation functions of scalar fluctuations in the scalar field. So it is often convenient to work with another variable known as curvature perturbations, which are actually freeze once they exit the horizon. So it is convenient to work with them, and we will express this power spectrum of scalar fluctuations as in terms of the curvature fluctuation in this manner. So similarly, you can compute 3-point correlation. Okay, 3-point correlations. If you have an interaction Hamiltonian at third order, you can compute the 3-point, at least the tree level 3-point correlation using this formula. So basically, you have to evolve the mode functions throughout the throughout the history, that is across the bounds and through the inflation, and you do this integral and you can compute the 3-point correlation. Again, this is the 3-point correlation of scalar fluctuations. What we actually want is to compute the 3-point functions of curvature perturbation, and you can relate the 3-point correlations in delta phi, which is the fluctuations in the scalar field, to the curvature perturbation to 3-point function in curvature perturbation. So we will talk about two quantities often interchangeably. So one is bispectrum. Bispectrum is basically the 3-point correlation of curvature perturbation sans the delta function, Dirac delta function. So this is a function of three wave numbers with one constraint, so 2 wave numbers. And we will also talk about the often the 3-point correlation of curvature perturbation is quantified by FNL, which is a dimensional quantity, which is basically the ratio of 3-point correlation to square of power spectrum. So as I said, we want to study this 3-point correlation as well as 2-point correlation in LQC. So the evolution, it depends on, basically we want to understand what is the evolution of perturbations throughout this background where you have a bounce followed by inflation. Okay, so so we can write the evolution of perturbations. This is the Mukhanov-Sasaki variable, which is related to the fluctuation in the scalar field using this formula, and it obeys a time dependent harmonic oscillator. And so to understand the dynamics, it is convenient, it is illustrative to compare k with behavior of root of absolute value of omega k. And so this is what is plotted here, root of omega on y axis, and this is the dark black solid line, and this is time, t equal to 0 is the bounds, and all these dashed horizontal lines are different scales, different wave numbers. So you can see that there are two scales that are characteristic in the problem. One is the scale called as KLQC. KLQC is actually related to the maximum value of energy density at the bounds, and Ki is the inflation, is the mode set during inflation. Modes smaller than Ki are never excited, so they are always super Hubble in the inflationary language. And the K star is the pivot scale, and here we will take K star to be 0.002 MPC inverse. So as you can see from this figure, if you have a mode which is lying here, that mode is that particular mode will always be much greater than root of omega until it crosses the horizon during inflation, or crosses this potential during inflation. So what happens is that for those modes, they are not sensitive to the what happens at the bounds. So those modes, those large wave numbers or small length scales don't feel the effect of the bounds, and they just are amplified during inflation. So those modes are expected to be scale invariant as you find in slow roll inflation. Now modes which are sensitive to this peak this potential or this root of omega during the bounds, they are comparable to they are modes that are comparable to KLQC or smaller than them. They will be excited during this bounds. So what will happen is that they will be excited. So by the time they reach somewhere here, which is before around the onset of inflation, they will already be in excited state. And not only that, if you look at correlations, they will also be non-Gaussian by the time they reach before they reach the onset of inflation. So what happens is that the job that inflation does is they amplify whatever has been set during the bounds. So modes which are sensitive to K, which are comparable to KLQC, will be excited. They will not be they are not expected to be scale invariant. Okay, and there are these modes which are K much less than Ki, they are never excited, so they remain in the Minkowski state because K is much smaller than this, so B is proportional to the potential. Okay, so as in terms of curvature perturbation, they are not amplified. So this is the qualitative picture that you can understand from this analyzing this equation. and that is what we numerically find also. So what we do is we impose initial condition somewhere here, where most of the observable modes are adiabatic, or k square is much greater than omega, and we evolve the perturbations through bounds across the inflation and compute correlations. I mean, sometime later during inflation. Okay, so this is what we do, and these are the numerical results. So as I mentioned, so this green dashed line is the slow roll result. So modes k, which is much greater than k LQC. K LQC is denoted by this vertical dashed line. They are scale invariant because they don't feel the effect of bounds at any time during their evolution. Modes which are comparable to k LQC or smaller get amplified, and the modes which are smaller has this modes which are much smaller than ki or comparable are not amplified. So this is the so these are the observable scales. So most of the work in which analyzes the power spectrum of LQC are done with the hope that perhaps we can this portion of the spectrum will leave some imprints in the observable universe like CMB. Now, so let's look at primordial non-Gaussianity. Primordial non-Gaussianity, as I mentioned again, mentioned earlier, the large scale modes are not are scale invariant. Large k are scale invariant, so they have slow roll like spectrum. Modes which are sensitive or which are comparable to k LQC or smaller are not scale independent, so they are actually oscillatory, and as you can see from the amplitudes, they are highly non-Gaussian. And there is one more thing that you can see from here. This is that this departure from scale invariance starts at around this wave number, whereas power spectrum for power spectrum the departures from scale invariance arises here. So you can see that FNL is actually more sensitive to, or 3-point functions are more sensitive to the bounds than the power spectrum. This is expected because you are actually integrating through the bounds in computing the 3-point function. Okay, so now our goal is to take this bispectrum and compute the reduced bispectrum, which is observed in CMB. So the idea is that you have to, so in order to compute reduced bispectrum, where this x, y, z are either temperature or electric polarizations, you have to do this 4-dimensional integral, one integral over k1, k2, k, I mean 3 integrals over wave numbers and one integral over x. So you have to do this 4-dimensional integral. So if I take the numerical calculation, such a bispectrum, and try to plug it in here and then do the calculation, then what my problem is that for each k I have to do the numerical simulation, and there are even if it's a very flat constant FNL, for each k if I have to do the not constant, very simplistic FNL, and if I have to do it for each k, it is time consuming, and in this case it's oscillatory. So if I have to resolve the numerical bispectrum, it's going to be tedious. So what we did is we try to estimate come up with an amplitude, come up with an analytical template to explain the bispectrum. So this is the bispectrum, right? So primordial bispectrum, this is what we have. So you can split it into two parts. One is you have a near scale invariant part, which is the slow roll part, or we will call it the local part, and then oscillations with some shape on top of it. So we will split into two parts. So the local part is easy to simulate, to model. So we just take the local template. So with a constant value of FNL, FNL set to 10⁻². Okay, and then you have this local template. So that explains the local part. Now how do you estimate this behavior? So what we did is, okay, so bispectrum has basically an integral. Okay, so you can roughly write it as Vk by Z. There are 3 modes which are you are computing the bispectrum at the end of inflation or later towards later part of inflation. So you have an integral from eta I to eta f, and inside the integral you have a term which is time dependent, and then you have a function of mode function, maybe it's derivative or mode functions. So what we did is to simplify the whole thing. So you keep the time dependence term as such, but you say that maybe this function, all I need to care is just simplify this by product of the mode function. Of course there will be some functions of factors of k square and all. For now we are just ignoring it, and we will see what we get. And then we also assume that Vk is basically given by e raised to minus ik eta. Okay, so this is true when k is much larger than KLQC, but not true in general. But we are going to simplify this by e raised to minus ik eta. So if I do this, plug all these assumptions in, my integral that I have in the bispectrum expression can be written in this manner. And I am also only interested in the portion around the bounds, because I am interested in finding the contribution from the bounds. So I have an integral from minus eta naught, which is some time before the bounds till some time after. And of course I extend that integral to minus infinity to infinity by introducing a window function which only selects that time regime around the bounds. Now the good thing about writing this integral in this form is that I can actually use Cauchy residue theorem to evaluate it. Now basically Cauchy residue theorem tells you that you just have to look at the poles of this G, and whatever the poles are, you compute the residue from that. So G can have either a real pole or an imaginary pole. If you have a real pole, then this is just oscillatory, but if you have an imaginary pole, you will get the sum shape. Okay, so you look at, so the motivation is what is the imaginary pole. So if you get the imaginary pole out of it, then it will, so remember this is all done with an eye on the numerical result. So you know that it has some behavior which is decaying, and then the oscillatory part also. So that pole, if the real pole will account for the oscillatory part, and the imaginary pole will account for the decaying behavior. That is expectation, or that is so what we can see is if G has a scale factor at the denominator, and then because A is a minimum, you can see that there is definitely a pole which is actually imaginary, because if you Taylor expand the scale factor, you can see that eta is equal to root of minus A by A double prime evaluated at the bounds. Because it's a minimum, A double prime is positive, A is always positive, so that is an imaginary pole. And there is some analytical expression that you can compute for the scale factor around the bounds and use that to extract the pole. And you get that the pole is located at this value. And we say that the scale dependence, okay, so now if you compute the residue, you plug it in the pole in this eta, and then you can say that the scale dependence of the imaginary, so if scale dependence of the bispectrum is basically this, okay, at least the decaying part from the imaginary pole is this, okay. This is a overly simplified way of looking at it, but we'll see. So then there are other things. We don't actually play with the oscillatory part, but we just include an oscillatory feature by saying that the oscillations are modeled by sine of k1 plus k2 plus k3 divided by, and the scale of oscillations is ki, which is the lowest value of ki that is excited during the bounds as well as inflation. And there are these modes which are evaluated at the end of inflation, and we just replace them by the power spectrum. And then if you put all of them together, you can compute, you can express the bispectrum in this form, okay. And here there are power spectra, so because power spectrum are also numerical results, so we want to substitute by analytical result, so we give this power law, pieces of power law, broken power law kind of thing. So putting everything together, we have this bispectrum. Of course, computing the FNL, and of course, how good is the analytical? Because we have used a simplified argument to compute the bispectrum, but what we find is that the analytical template actually explains the primordial bispectrum quite well. So now the challenge is to compute reduced bispectrum. And what we, so the good thing about this template is that it has, if I have an integral over k1, k2, k3, none of them speak to each other. So I can separate them out. I can do the k1 integral separately, k2 integral separately, k3 integral separately. So I can do that, and I can express, so 4-dimensional integral actually splits into one integral over x, and then another integral over k. So I just have to do the k integral once, and then I have this. This template also has a separable property, and we compute the reduced bispectrum. And what we find is that this is the contribution from the local template, and this is the contribution from the highly oscillatory part. So it turns out that because of the high frequency oscillations in the spectrum, the k integral over k will actually wash them out. And so we see that Even though primordial bispectrum is non-Gaussian, the observed reduced bispectrum will be consistent with whatever we have observed today. We have repeated this for TTE and EEE correlation, and we get similar results. So I'll leave you with the summary. So in LQC, the primordial perturbations are Gaussian, are non-Gaussian, yet at the level of reduced bispectrum, it is Gaussian. So, thank you.
Thank you. So maybe one quick question.
Okay, I'll just repeat what we
yes,
discussed a couple of weeks back when you came. So the signal you have is fairly large. It's just that there's a sine problem, you know, sinusoidal oscillation, right? So there's nothing that compels you to measure only bispectrum as defined by the general community. You can always define a quantity where this signal is actually added up, and the challenge would be to now look for that in the data. I mean, to me, it's a eminently doable thing, and it's a huge signal. So I think, I strongly feel that you should look into it. I mean, it's just, to me, it's very, very doable.
Yes.
LQC models, what of inflation, what do you get for R?
That depends on the tensor, potential.
So,
that you
but,
have.
so this model doesn't make any ab initio prediction for R?
It depends on, because there is a inflation. Inflation follows after the bounds. No, so the tensor to scalar ratio at whatever scales we are measuring will depend on the model, underlying model.
Okay, so it depends on the inflationary model also.
Inflationary model.
It doesn't depend on the
doesn't,
LQC details. Okay.
Okay, let's continue the discussion to the tea times. Let's thank the speaker again. Next speaker is Ratul from IISc Bengaluru. Uh, 12 minutes plus 3 minutes discussion.
Good morning, everyone. I think we have already discussed about the fact that this whatever we see in CMB, the anisotropies into CMB, and the large scale structure that we see today are basically originated as quantum fluctuations. So in this talk, I basically briefly explain the quantum evolution of these primordial fluctuations. Okay. Yeah, actually these quantum fluctuations are everywhere. These vacuum fluctuations are everywhere. So they are simply oscillating, locally oscillating in a potential well, right? So around the minimum. So they are just simply, oscillating, relaxing comfortably. So in order to, make them useful to do something, someone has to pull them out from the potential well, right? So this is what inflation does. So this is something usually, Sriram used to tell to me that if you want to become something, you have to come out of the potential well, and you have to come out of the, comfortable place. So this is what inflation does here. So there are fluctuations, quantum fluctuations, and the inflation just pull the fluctuations out of the potential well. So during this inflation, the horizon of the universe expands exponentially, but the Hubble radius, which is actually the measure of space-time curvature, that remains almost constant. And the wavelengths associated with these quantum fluctuations also increases exponentially. So what happens is that these wavelengths become larger than the wavelengths associated with these fluctuations become larger than the Hubble radius. So it starts to see the curvature of the space-time. Okay. So this is the Hubble radius. So this is the wavelength associated with the fluctuation. Some of them are inside the Hubble patch and some of them are outside during the evolution. And when this length scale associated with these fluctuations become comparable to the Hubble radius, which is a measure of, as I said, which is a measure of curvature of the space time, comparable with the length scale associated with the Hubble radius, then we start to see the geometry of the space time, which basically means that these fluctuations start to interact with the background, and then okay. So basically is that, so during this evolution of fluctuation, inflation makes that associated with fluctuation. So as I said, it's a potential well when simply oscillating, it becomes inverted. The potential becomes negative. So the oscillator becomes inverted oscillator. So in inverted oscillator, we know that the fluctuations simply grow or decay. So in reality, so we deal with not the harmonic. What we have is each point in the space infinite number of oscillators. So we cannot simply talk about the one oscillator and do the physics. So we have to take the average over a path, average of amplitude of fluctuations over a path, and do the physics. So here these are the small patches inside the radius, and then this dashed, this circle, white circle, size of the Hubble radius. So when this, as I said, when the length of these fluctuations become larger than the Hubble radius, we start to see the curvature of the space-time. So when this the patch size of the patch becomes larger than the Hubble radius, practically we can show that these patches become independent and evolve independently without interacting with other patches, like separate universe, separate homogeneous universe. Okay, so that is what happening during inflation. So we have now separate universe evolving independently. But when the universe goes to the radiation dominated or matter dominated, the horizon becomes almost equal to the Hubble radius. So these patches become inside the horizon. So they start to form, different structures. So this is the story of, the quantum fluctuations. How these quantum fluctuations become the structures in the universe. Okay. So this is just a story. So the physical question we ask is that how much quantumness. So as I said, these are original quantum fluctuations. How much quantumness, they remember about their quantum origin. So we calculate this or we analyze this correlation functions at the end of inflation or radiation domination or matter domination. So they are classical correlators. So the question is how much these patches or different structures know about their quantum origin. Okay. So there are different measures available to quantify the quantumness. Some of them are skewing, and skewing basically that if in phase space if we calculate the correlation functions, how much the dispersion in one of the direction is larger than the other. So that is what skewing means, and we can measure the skewing in terms of this parameter. That is one of the measures, and there is this, we can measure the quantum using quantum correlations. That's the entanglement, quantum entanglement. There are measures like quantum discord, entanglement, etc. So these are the quantum measures. So how do we do the quantum mechanics here? So as I said, we have fluctuations. So usually these fluctuations are the amplitude of fluctuations are described by Muganow-Sasaki variable V, and this is the Lagrangian associated with this Muganow-Sasaki variable, and this alpha is basically the as I said, these fluctuations interact with the background when the size of the fluctuations become comparable to the Hubble radius, right? So this alpha is the interaction of this fluctuation with the background. and this is the whole Lagrangian associated with this the amplitude of fluctuations. Okay. So this alpha basically the function of time, which is a function of explicit function of scale factor, which is how it determines the distance between the 2 points in the universe and rate of expansion of the universe and its derivatives. Okay. So the simple thing one we can start is of course we have to do the quantum mechanics in real space, but the simple thing we can start with study the quantum mechanics in Fourier space, right? What is simple here is that all the fluctuations, all the I mean, if you decompose the fluctuation in terms of Fourier modes, all the amplitude associated with these fluctuations evolve independently. Okay, so we can study the quantum mechanics of each mode separately. We can associate this quantum canonical, I mean the computational relations separately and study the quantum. Okay, so in Fourier space, the Lagrangian is just this. So this is a Lagrangian associated with the production of two particles, particle going in k direction and particle going in the minus k direction. So if you see, the one of the main problem working in Fourier space is that the V, the amplitude of the fluctuation V in Fourier space is not Hermitian. Okay, so in real space it is Hermitian, but in Fourier space it is not Hermitian. So, but in order to analyze this, quantum mechanics or the evolution of fluctuations, quantum evolution of fluctuations, we need to work with Hermitian operators, right? So one thing we can do is that just split the Mugano-Sasaki variable into real and imaginary part, and work with real or imaginary part separately. That is one thing. Or we can make different real operators from the space phase variables like Mugano-Sasaki variable and from the momentum, and work with those canonical variables. So if you work with real and imaginary part of the Mugano-Sasaki variable, what we get is the Hamiltonian associated with a simple harmonic oscillator for each real or imaginary part. But this harmonic oscillator is actually a time dependent harmonic oscillator. So we know how to do quantum mechanics associated with this time dependent harmonic oscillator. Okay. So if we take some other set of variables, say some other combinations of Mugano-Sasaki variable and associated conjugate momentum, then we can get different sets of real operators. Suppose we take this kind of, then we get this is one xk is basically amplitude of one oscillator and x minus k is amplitude of another oscillator, and pi is corresponding conjugate momenta. This is actually the two oscillator. The Hamiltonian is kind of Hamiltonian of a two oscillator interacting with each other. Then the interaction strength is actually determined by the alpha. Alpha is something, the coupling between the the fluctuation and the background universe. Okay. So basically this Hamiltonian gives entanglement because of this entanglement between this k and minus k. Yeah, so we can do this quantum mechanics in some real inflationary models. So in slow roll inflationary models, what we know is that this if you use that real and imaginary part of Mugano-Sasaki variable, then what we get is that in phase space, in slow roll inflation in space space, the dispersion towards the v square direction, the position direction will be larger than the dispersion along the momentum direction, which means that the state or the space phase is skews in one of the direction. Okay. Suppose we take another example like the slow roll, and there is an ultra slow roll and slow roll regime, which is a famous model for producing black hole, primordial black hole formation. So in this type of models, what is going to happen is that during the first slow roll, this phase space is skewed in one direction, and when there is an USR phase where this, and during that time this squeezing becoming in the other direction, to the momentum direction, and then the universe evolved into the final slow roll phase. There the evolution become again the squeezing becoming again towards the position direction. So this the entanglement entropy also we can calculate in the similar way, like we have to trace out the one of the system and find the entanglement associated with the one of the system and calculate entanglement entropy, and what we see is that it is proportional to the squeezing parameter R, which is, as I said, it has a devolution something like this. First increases, decreases, and increases again. So the entanglement is also increases, decreases, and again increases. So yeah, that's it. So I mean, this is the basics of quantum mechanics in a simple setup. But there are more things one can do. So we have explored different aspects of quantum mechanics in different models, like in multi-field models and when there is a magnetogenesis during inflation, and if we use the coherent state as initial state, we can do the similar quantum mechanics. But in in reality, we have to do quantum mechanics in the real space and find out how much quantumness is buried in the correlation functions in real space, right? So there are papers calculating this entanglement in real space, quantum entanglement in real space between the two patches in the patches in the universe, and if the distance between these two patches are larger than the Hubble radius, then the entanglement is almost 0. So that's what the result. But that is for the de-Sitter. So there are more things to do if you assume the slow roll, as Sriram said, that the de-Sitter is just an approximation. So if you do more realistic inflation, remote like slow roll inflation or multi-fleet inflation, bouncing model, what are these correlation? I mean, the quantum entanglement in the real space is still a open question. Thank you.
Any question?
Sorry, I didn't fully understand. So your initial question was whether the origin of fluctuations are classical or quantum.
No, it is quantum that we know. The question is how much quantumness is inside these correlation functions. So whatever we measure from CMB or in the last case structure. So that is the.
You were asking how much quantum it is.
Yes.
I see.
How to measure, how to quantify.
And this you are trying to quantify by some quantum entanglement. But what exactly the observable is? Can you just?
Okay, there is entanglement. These are derived from the correlation functions. So that we can construct one quantity called logarithmic negativity, which is actually we can construct from the covariance matrix.
From?
Covariance matrix, like from the correlation functions, and also there is called quantum discord. That is also one can construct from the correlation functions.
And they tell you about. So you don't have a like Bell inequality kind of a measure.
Yeah, that also one can do. So I forgot to mention in the slide. So that also we can do, but in continuous space, we have to. This is a continuous variable, right? So we have to construct a pseudo spin operators associated with because these are not spins, right? We have to construct pseudo spin operators.
So these are entanglement. What kind of entanglement? What space you are computing this entanglement?
Okay, these are entanglement between the two structures in the universe. Okay, so how these two structures in the universe are connected quantum mechanically?
No, I'm saying that is as you said, this is not spin space entanglement. So this is some momentum space in entanglement.
Yeah, so whatever I have discussed is in momentum.
The noise is just k minus k as of particles produced. They are entangled.
So here, whatever I have discussed here.
Momentum conservation.
That is, yeah, exactly.
So I'm saying that even in classical physics, there is the same from momentum.
No. These are quantum states, and there is an entanglement between those.
So this entanglement generation is due to the expansion of the universe. This alpha. That's it.
Maybe over
So you have an alpha term which is a coupling between Vk and Vk prime, or in other words V and momentum, right? So you can always do a canonical transform and then make it diagonal, right? And so then so classically they are all equivalent, whether because canonical transform doesn't change the system. It's just different variables. But quantum mechanically, you are saying that they will be very different.
No, quantum mechanically, I am not saying they are different, the measures will be different. So, actually if you use this real and imaginary part of Mugano-Sasaki variable to study the quantumness, what we get is the phase space is squeezed. Okay? So, this squeezing is manifested in the other set of variables as quantum entanglement. Both are quantum mechanical quantities, measures, but it is manifested in different avatars, that is it.
Another question is, you studied the ultra slow roll. So when you have coupling between Vk and Vk prime, so one is a growing mode, which is actually a constant mode, and a decaying mode. So this will introduce entanglement between the constant mode and the decaying mode.
No, actually here I am talking about the entanglement between k and minus k.
Yeah, that is fine,
Right.
but in USR maybe you will have such a thing.
No, there is no coupling between decaying and.
No, when you compute Vk prime, the decaying mode will be the dominant one. So will there be coupling between them? There will be, right?
No, one thing is that we have to associate this canonical commutation relation between two systems, right? So there is no such association, this canonical commutation relation between these two modes, right? Those are not independent, I mean those are the same.
Thank you.
I have a very naive question. So, of course, during inflation, this perturbations are being generated quantum mechanically. But at some point of time, it has to become classical, right? So the general notion is that when it becomes super horizon, so the squeezing parameter will be very large, and it will become classical. So whatever Jerome Martin and Vincent has seen here, that there is no entanglement, it is a signature that these perturbations have become classical upon super horizon modes, right? So how do you measure the quantumness of the of the modes which have been generated in the sub-horizon mode? Because once they cross the horizon, they has to become classical, right?
Okay, so they has to become classical. That is approximated statement, no? Like.
No, but if it is not becoming classical, then how it can seed classical structures?
That is true, but I mean the dominant contribution is classical, coming from the classical correlation functions, but there can be quantum correlation functions. But as you said, from these papers, what they are analyzed is that how much quantum entanglement is there in real space correlation between these two patches or two different points in the CMB. So they are saying that in de Sitter limit, so there is no entanglement if the the point is, the distance between the 2 points is larger than the Hubble radius. Yeah, that is true. So in principle we cannot measure.
Yeah.
Okay.
Okay.
But if you do for slow roll or some other models, I don't know, there may be some signatures.
Where is the next speaker? Okay, so then we'll move to the next speaker. So let's thank the speaker again. The next speaker is Subhashis from IISER Pune.
Okay, am I audible? No? Okay. Good morning everyone, and thank you to the organizers for this invitation. I am Subhashis Maiti from IISER Pune, and do not get confused by the name. I am other Subhashis Maiti than the one spoke on Monday. So you both are sitting in the same room basically. So today I will be talking about decoding the phase of reheating with the nanograph 15 years of data. So this work has been done in collaboration with Nilanjan Dev Bhaumik, Mohammad Riazul Haq, Devaprasad Maiti and Professor Sriram Kumar. So let me just briefly introduce like what I will be talking about, what's the motivations. So I mostly work on the epoch of inflation and the subsequent phase of reheating. So what's the inflation? So cosmic inflation is basically an accelerated expansion of the universe at very early stages. And one can show that this accelerated phase can be derived by a single canonical scalar field minimally coupled to gravity, where this is the potential, this is roughly the potential how it looks like. Now, by far we have already seen this kind of potential many times in this seminar. So, what I am interested in here, so let us see, this is the slow region. So, what are we need? We need sufficient amount of inflation, like roughly 60 fold. So, this tells us that the field has to roll slowly down to the potential. Now, during inflation, we know that we also have the perturbation generated naturally during inflation, which at the later time gives rise to various observables that we see today in the present universe. So, there are scalar perturbations generated, there are tensor perturbations generated, where tensor perturbations are also known as the gravitational wave. What I have plotted here on the right side, so this is the 2-point correlation of the power spectrum, of scalar perturbations. Now, on the large scale, we have observations of CMB that constrain our scalar perturbations over the large scales here on this. And the large scale corresponding to the modes which leaves the Hubble radius during inflation at the very early stages of the universe, inflation, and which constrain the early stages of the inflation like roughly 10 to 15 epochs of inflation. But the dynamics of the later stages of the inflation are still poorly understood. So, there might be like scenarios where some non-trivial dynamics can be happened over the later stages. Now, what particularly we are interested here is this kind of scenario, you can see there. So, here we can see that in this region the potential of the inflaton becomes extremely flat. So, in that situation what happens that the speed or the velocity of the inflaton field becomes extremely small, which is also refers to as ultra slow roll inflation. And this is kind of a model that just Ratu spoke about, that the two slow roll region, and there is one ultra slow roll region that is sandwiched between two slow roll region. And this is very famous picture like to generate this kind of PBH and secondary GW. So, what it does is that if we have this kind of scenario, we get that the power spectrum, the scalar power spectrum will have an amplification or have a large strength over the small scales, larger like almost of the order of at least 10 to the power 7 times larger than what we have on the CMB scale. Now, why do we need this kind of power spectrum? Well, I just said that this kind of scenario actually is very important in the context of PBH formation and the generation of secondary gravitational wave, which I will be talking about in this talk. So, before going to the analysis, let me just quickly tell you about what are the assumptions we have taken in our work, in this work. So, we have considered that we did not take any numerical power spectrum in this work, rather we have considered an analytical power spectrum which has a nearly scale invariant part here, and it has a rise of k to the power 4 kind of stuff, and then it drops as k to the power n naught. We have also considered that during reheating the equation of state of reheating will be constant throughout the reheating, and the transition from reheating to the radiation dominated epoch is sudden. So, with that first let me explain what PBH is. You already heard, but let me just summarize still. So, what happens during inflation, that all the perturbations grow and go to the super Hubble region. After the end of inflation they re-enter the Hubble radius, and if we are talking about scalar perturbations, what it does is like they accumulates matter and create overdense regions. Now, if the density of these overdense regions become above some certain threshold or critical value, which I have quoted here, the region collapse and form primordial black holes. This is famous picture known as base sector formalism. So, let me emphasize that this form of the delta C analytical we have taken from this paper. I should also say that there are also uncertainties in the calculation of this delta C analytical, which we will also take into account in our later work. Now, once PBHs are formed, they are cold and non-interacting in nature. So, they can act as dark matter. Now, fraction of total dark matter in the present universe is coming from PBHs, that is also what is known as this quantity FPBH. And if PBHs are formed during during reheating, This is what the form of FPBH will look like, where beta m is basically the abundance of PBH. Now, this quantity what I have plotted here for different parameter values. What I also want you to notice is the contour plots. So, they are basically the constraint on the maximum allowed value of FPBHs that is coming from various observations, and they are mass dependent constraints. So, with that, let me also move on to the spectrum of gravitational wave. So, yes, the dynamics of reheating will also have effects on the spectrum of gravitational wave for the modes that re-enter the Hubble radius during reheating. So, when we are talking about the gravitational wave, this omega GW is generally the quantity of observational interest, which is given by the ratio between the energy density of gravitational wave to the critical energy density of the universe, and this is the quantity I have plotted in this book. Where dashed line you can see here is basically the omega GW for scalar the primary gravitational wave, which is basically generated from the metric perturbation without any source, and this solid line which has this peak kind of nature is the scalar induced secondary gravitational wave, omega GW for the scalar induced secondary gravitational wave. Now, also this red dashed line you can see here is basically a constraint for coming from delta n effective bound. So, whatever we do, we have to take care that it does not cross the bound of delta n effective. Now, this kind of all the primary or secondary gravitational wave, they are basically primordial in origin. So, they are expected to be present in our current universe as a stochastic gravitational wave background. Now, recently PTA has like a couple of years back, PTA have observed this kind of stochastic gravitational wave background. After the data released, there are multiple efforts to explain this data in terms of with the gravitational wave coming from various sources, where the scalar induced secondary gravitational wave remains a promising candidate to explain the data. You can see here. So, now most of the work that that contains to explaining the data in terms of the scalar induced gravitational wave face one challenges, major challenges. What is that? That for the power spectrum, the corresponding omega GW that satisfy the data which is generated during radiation domination, that satisfy the data, it leads to overproduction of primordial black holes. So, in this work our goal was to explain the data with our model or our scenario, where gravitational wave is producing during reheating without leading to any PBH overproduction. So, to do that we have run our analysis to compare our model generated the gravitational wave with the data. We have used the publicly available code PTRCAD. What we have first done, we fixed the temperature of reheating at a very low, which is 50 MeV, and we have run 4 analyses. And the first analysis, which is a 4 parameter free run, we have 4 parameters, 3 power spectrum parameter, which is the position of the peak, amplitude of the peak or the strength of the peak, and the spectral index of the decreasing part, and also the reheating equation of state. Now, after the first run, what we see that our analysis has a very weak dependence on N naught. So, in the next run what we did, we actually, which is known as the 3 parameter free run, we fixed the value of N naught to -2, and we have run with peak, K peak, A naught and WRU, and we see that it kind of resembles this kind of nature in this plot. Now, till now whatever we have done, we have not imposed any kind of constraints over on our run. So, we expect that there might be the problem of PBH overproductions, which were our concern. So, to overcome that, what we did, we mapped our variable from power spectrum variable to the variable of primordial black holes, which is the mass and FPBH. And in the third run, which is 3 parameter bound run, we run with M, FPBH and WRE, and what we did, the constraint was that FPBH cannot cross more than 1. And also in the fourth run, we have run with 2 parameter, which is M and WRE, and we have fixed the FPBH to the maximum allowed value here, the mass dependent constraints, we have fixed the FPBH to that. And after the run, we get this result. And also I want to emphasize that I have said that there are also uncertainties in the calculation of delta C. analytical. So, to take into that account, we have also run with 0.5 delta C analytical and 1.5 delta C analytical. And we see that for delta C equals to 0.5 delta C analytical, most of the allowed region like parameter space are omit because of the PBH overproduction. Okay. So, this is the parameter base fit parameter values that we got from our analysis. So, let me just go through the results. So, yes, this is the spectrum of omega GW using these base fit parameter values, and this is the corresponding FPBH. What you see that this green and red curves are corresponding to the runs, the first two runs, which are the free runs. We said there are actually the problem of PBH overproduction, where FPBH is greater than 1, you can see, which we have overcome with the next two runs, which are given in this red and blue curve. Now, how good is our model? We wanted to see. Our scenario is to do that, to check that. We also performed a Bayesian analysis compared to the astrophysical model, SMBHB model. Yes. So, we saw that for delta C equals to 0.5, delta C analytical and 1.5 delta C analytical, we got a large Bayes factor. So, you can say that our model is well favorable. So, with that, let me just summarize that. Yes, scalar induced secondary gravitational wave generated during the epoch phase of reheating can satisfy the nanograph 15 years of data without leading to any problem of PBH overproduction. Thank you.
Thank you.
So,
thank you for the very nice talk. So I had two quick questions. So one is, in your model, can you introduce PBH spin?
We haven't thought of that. I think that can be done. I'm not sure like what extra we will get from that, because in this analysis our role was like our aim was just to explain, see that whether it can explain the data without any overproduction. But I'm not quite sure if we include the spin of what modification we will get.
And the other thing is, so when you introduce this model, how fine-tuned your parameters are?
Oh, okay, it's not that much actually. So there's no model actually. If you can see is that so we have an analytical power spectrum. So we have a range of parameters with which we have run. So that's all. So model you means the we need to construct a like potential. We do not have a potential in this curve. Many can be constructed if we have the power spectrum.
Okay. Okay. Thanks.
Yes.
Okay, hello. Yeah, generally in your model, the P curvature power spectrum goes k to the 4 when it's rising.
Yes.
Generally, gravitational wave proportional to P earth square. Okay, omega GW is proportional to P earth square with some integral.
Yes.
But nanograph predicts typically the spectral index of the GW around 2.
Yes, yes.
So there is, but your curvature.
So this is around 2 actually. So if you
what is the physical reason that this scalar goes k to the nearly k to the k square, where your power spectrum typically goes k to the 4, when your source term typically goes k to the 4,
yes,
but your GW goes k square. You get my point?
Sir, are you asking whether k power 4 is
power
necessary to get k square in omega GW?
Yes. For this kind of scenario, generally source is goes k to the 4.
So there is no analytical calculation that is done very recently by Chinese collaborators.
do you have
Yeah, that can be shown analytically. That's what you're asking.
Yeah, but the source is much steeper than the GW, no, in these scenarios. So there's suddenly.
That depends on the transfer functions,
etc. So this is the actually expression for this omega GW. It's very complicated to.
And it means it always goes nearly k square behavior, or it can be changed. Like if
most ultra-slower model, it is k power 4 rise in the power spectrum.
But I am talking about the spectrum of the GW sourced by.
Imagine it, because it is ultra-slower models, it should also behave in the same manner.
Oh.
But I need to check that.
It will change a bit, like if we have a different WRE, but it won't affect that much.
I'm talking about radiation.
Radiation, okay. So,
Just no. What is the physical? Because source is goes k to the 4.
so he's saying that this
The
PR,
potential
this
GW
tau
is
PR is k to the
square.
power 4, then why do we have
K
omega
square
JW
behavior.
that is k square?
Generally, in case of magnetic field, generally we have seen that they are the square of the NB, but in this case there is a difference of the spectral nature of behavior. So
That should be possible to show.
Yes, yes.
Probably-
So I'll try to check that.
Yes. So Ashish, here. So that reheating temperature, is that quite low?
Okay. So why did you choose that? Okay, let me just. So basically, we wanted that the corresponding mode that we enter the Hubble radius that correspond to the this nanograph band. So if we consider the reheating temperature that low, that's only when the k corresponding to the mode will lie somewhere around here. So we wanted our window that lies in the reheating epoch, window of PTA band. If you increase the reheating temperature, it will somewhere like around here or here. So that's nothing but compare like calculating in the time of radiation domination.
Okay, if no more question, let's thank Shivashish and all the speakers in this session. So tea time now, and we'll come back at 11:30.
Sorry?
So Yogesh, so we'll start in 2 minutes or like this, give some time to ask.
Yes. अभी वो तुम डिसाइड करो. Depends on.
Give you a 5-minute warning, 10 minute?
5 minutes.
5 minutes is good.
Yeah.
So it's total 20.
Total 20. So I think 17 plus 3 is the breakup.
Okay, so I'll give you a 10-minute warning, and after that, if you can finish in 5 minutes, after that we'll leave 5 minutes for questions. Is that good?
Yeah, that's also okay.
Yeah. Or at least you can leave some.
So if you,
minutes.
so they say 17 minutes. So
Okay.
if you
Yeah, you
finish,
can
if
leave
you give
some-
me 12 minutes, if you give me a warning, I'll finish by 17.
I'll give you 10 minutes.
Okay.
And after that, you can finish in like 6 minutes.
Okay, I'll keep track.
So I'm motivated by not having anything other than 10.
Okay. There's a 5.
But we need something more than 5, but less than 10. That I could do. Okay, let's get started. And we have first Yogesh, who is going to be telling us about galaxy evolution.
Yeah. Thank you to the organizers of this meeting for inviting me to give this talk. I'm going to give you a slightly different perspective from most of the other talks you've heard. It'll be quite related to what Shriyanand spoke about yesterday. I'm going to define cosmic dawn as redshift 14 because that is the redshift at which we have the highest confirmed spectroscopic redshift of a galaxy. And redshift 3 is just arbitrarily defined as cosmic noon. You can choose z of 2 or z of 1.5 if you wish. So if you look at JWST, the key thing to remember is that it allows us to probe the rest frame optical band between 400 and 800 nanometers at relatively high redshifts for the first time with HST-like resolution and even better sensitivity. So therefore, for the first time, we are able to trace the bulk of the stellar mass which lives in the older stellar population, which emits in optical and near infrared. We are able to probe that for the first time. Rest frame optical is also less affected by the presence of dust compared to the rest frame UV. And what it enables now is that the techniques and technologies that optical astronomers have used for 100 years in studies of local galaxies in the universe at redshift 0, these techniques can be now applied, directly applied at redshifts 3, 4, 5, 6. JWST has a number of instruments. There are 4 in number. NIRCam is the near infrared camera, which goes from 0.6 to 5 microns. Corresponding to that is the near spec, which is the spectrograph. It's a multi-object spectrograph. It can do 100 plus targets via microshutters. It spans this wavelength range, and using PRISM and GRISM, it has 3 different resolutions at which it can operate. There's also NIRIS, which allows you to do slitless spectroscopy in the near infrared. And for the mid infrared, it has a do-all instrument called MIRI, which operates over a fairly wide wavelength range and does both imaging and spectroscopy. If you're interested in race frame optical lines, then H alpha will enter the MIRI band at redshifts greater than 7.5, and of course it's quite sensitive to warm dust emission. A number of surveys have been carried out, galaxy surveys have been carried out with JWST, and it is so sensitive that you can reach absolute apparent magnitudes, AB magnitudes of 30 in various fields, and this enables the detection of extremely faint, very high redshift galaxies. These are some of the surveys which have released data. There's a very short proprietary period for JWST data. So all of these surveys either have public data in some partially reduced form. Many of them have fully reduced data and catalogs, etc., which are publicly available. So over the last 3 or 4 years that JWST has been in operation, it's made a number of surprising discoveries. So the first thing it found is there were too many disk galaxies at high redshift. And you saw an example on Monday when Rashi spoke about the Alaknanda galaxy. And if you go and get integral field spectrum of those galaxies, you find that many of them are regular rotators. This was not expected. Then it also found too many massive galaxies, too many luminous galaxies, too many large galaxies, too many high metallicity galaxies, and also too many massive dusty galaxies, which is a class by themselves. We call them red monsters. In addition to this, it also found too many massive yet quiescent galaxies. So these are referred to as post-starburst galaxies. So these are galaxies that in a very short period of time not only have formed a very large number of stars, but have also gone quiet. So it's like they've created a lot of stars, but after that they begin to look like quiescent galaxies when seen. Then of course there are too many compact, massive dusty galaxies. This again turned out to be a new class of objects. These are the so-called little red dots, believed to be very compact AGN, and they're very dusty and so on. Lots of challenging problems that they pose. And then there are too many protoclusters also that are seen. I will not talk about the last bullet point, but I'll cover some of the others. So Rashi showed you Alaknanda on Monday. This is an even more surprising galaxy called the Big Wheel Galaxy, because it's in many respects like the Milky Way. It has the same diameter as the Milky Way. It has the same stellar mass as the Milky Way. It rotates like a disk, just like the Milky Way, at speeds comparable to the Milky Way. And the only difference is this particular object is at a redshift of 3.25 when the universe was only 2 gigayears old. It's, as I said, stellar mass and size indicate Milky Way-like properties, very, very clear spiral structure. The only major difference between this galaxy and the Milky Way is that this galaxy is at the moment, or when it at that point, at that redshift, is forming stars at a rate about 30 times larger than the Milky Way. Okay? So it's an exceptionally star-forming galaxy. It's also located in a fairly dense cosmic environment. So this seems to suggest that favorable conditions for large disk formation in dense environments in the early universe were present. But to me, to form a Milky Way-like galaxy, fully with spiral arms, bulge, disk, everything, rotating, and to do assemble 10 raised to 11 stellar masses within 2 gigayears is really, really difficult to explain. So in the early days, of course, JWST produced a lot of photometric candidates for high redshift galaxies. And typically, so there was a survey called SEERS which found galaxies within this redshift range, and these candidates are typically very compact, mean half-light radius, median half-light radius of about half a kpc, and they're fairly UV bright, okay? And the UV luminosity function was also explored between redshift 11 and 9, and all of them seem to exceed the lambda CDM based predictions of galaxy formation. The possible implication was what you've heard already from several talks, that maybe there's a top heavy IMF, maybe there's extremely efficient star formation, but this star formation cannot be continuous. It has to be efficient, but it has to be in short-lived bursts. The dust levels have to be very low so that most of the UV photons can escape the galaxy. But it was also realized very early on that photometric redshifts can be quite unreliable. The little red dots, for example, were originally thought to be extremely low dust but extremely high redshift galaxies. Turned out they were not at redshift 15 but more like redshift 5 and much more dusty than thought. This is an example where you have photometric redshifts estimated for the same galaxy using a limited set of broadband filters on the left column, and here you have a much more densely sampled set of filters. These are the so-called medium band filters, and if you look at the redshift of this galaxy determining using this data and that data, the redshifts turn out to be very different. And the numbers here, there's also a spectroscopic redshift available, and it turns out that if you go from here to here, then many of the degeneracies, for example, there can be a drastic degeneracy of you mistake the Balmer and Lyman breaks. And here the photometric redshift, the spectroscopic redshift is 2.69. With this data you get a redshift of 0.19, and with this data you get a redshift of 2.71, which is quite close to the true value. So things can be drastically wrong, big mistakes could be made and were made in the early days. But now with this addition of medium band filters, the reliability of photometric redshifts has been greatly improved. But of course the golden standard is spectroscopic redshifts, and now we have redshifts at 14 or so. This is a paper from last year by Carniani et al. In Nature, and they found two galaxies at redshifts around 14, and they show sharp Lyman alpha breaks and negligible emission lines, placing them at about 300 million years after the Big Bang. The brightest is very bright. It's also spatially resolved. And what they said is, say in the paper is something I've quoted, that the excess of luminous galaxies in the early universe cannot be entirely explained by accretion onto black holes. Okay, there has to be star formation, considerable star formation happening there, and therefore galaxy formation models will need to address the existence of such large and luminous galaxies so early in cosmic history. So these are the spectra of these two galaxies. You can see that sort of blue world of about 1.8 microns or so. There is the Gunn-Peterson trough. You can't see the galaxy at all, but once you go redward, you begin to see the galaxy, as you can see in all of these bands. The spectrum is exceptional. I mean, to get a spectrum of this quality at redshift 14 would have been unimaginable with any other telescope. But now with the prism mode of JWST in NIRSPEC, we are able to get these spectra. Not only that, we are able to follow up these galaxies with some other instruments. So ALMA is a very, very sensitive instrument, and in the far infrared, one of these two galaxies was detected in the O3 line at 88 micron, and that gave you a very precise redshift, which closely matched the break-based redshift that you had from JWST. And this galaxy was found to be surprisingly metal-rich, but it was extremely dust-poor. So it doesn't have dust, but it has some of the other metals in large quantities. You can also follow up this and other galaxies with the MIRI instrument on JWST, And there you can get H alpha detection and therefore a fairly solid redshift. The implications of these objects is that rest frame optical spectroscopy of Z greater than 10 galaxies is feasible with the JWST MIRI instrument. We see lots of rapid ISM enrichment and extreme conditions prevailing in high redshift galaxies. You also find what are called these red monsters. So in a paper in Nature, as part of the FRESCO survey, they found 36 dust obscured galaxies within this redshift range, and among these 3 have fairly high stellar masses, again above expectation. So many of these papers invoke extremely high star formation efficiencies. 50% of halo baryons in stars are getting 50% of the halo baryons are getting converted to stars. This is 2 to 3 times more efficient than even the most efficient conversion that you see in low Z galaxies. This is a result that I sincerely doubt. There is something funny going on here for sure. Because these objects by themselves are expected to contribute 70% of the cosmic star formation rate density at a redshift of 6, indicating that efficient dusty starbursts in the early universe were quite important as a source of ionizing photons. So this is an image of the 3 of these galaxies. As you can see, it's extremely bright in the reddest 4.44 micron filter, but if you go to shorter wavelength filters, the galaxy has completely disappeared, and here you can see a clear H alpha detection of these objects. Then quiescent galaxies at high redshift. So Karnal in a paper found a galaxy, extremely quiescent galaxies at redshift 4.65, no emission galaxies, lots of absorption galaxies, lots of Balmer absorption lines indicating recent end of the starburst. And so now people have found more, 10 massive quiescent galaxies at a redshift of between 3 and 5. And again, these are 3 to 5 times higher than pre-JWST models predicted, indicating that massive galaxies formed and quenched very rapidly, at least in some parts of the universe. So this is that post-starburst galaxy that I was mentioning. This has a very, very blue UV continuum. The absorption lines are very, very clear, which means that although it has a blue continuum indicating a strongly star-forming galaxy, star formation is actually recently quenched here. And that is why you are seeing a number of strong absorption lines over here. So again, strange, it built up enormous stellar mass in a very short period of time and then went all quiet all suddenly. So what is being increasingly invoked in order to explain the mismatch between the observed galaxy luminosity function and the prediction from models is what is called bursty star formation. And the idea here is that these galaxies are forming stars, but they are forming stars very efficiently, but only for a very short period of time. Then the star formation switches off. Then again it starts after a period of time. And this is what allows you, like I'll just focus on this luminosity function, and you can see this is at redshift 12 that the observed data, the points in gray are photometric redshift data, so you can ignore them for the moment, but there are spectroscopic redshift based data points, and you can see that the burst without dust gives you a fairly good approximation for the data points. So this again will need to be explained. I mean, it's easy to say that the star formation is bursty, but what is the physics that allows for this kind of star formation? Because we don't see it in the nearby universe. So there is some tension with galaxy formation models. So these early quenched galaxies, these ultramassive dusty systems at redshift 5, all of these appear to be in tension with simple models that have been tuned with HST data. And obviously galaxy formation models will need to be modified for these early epochs. So initially there was a lot of talk about new physics, but these were probably premature for the reasons that I tried to describe. So what are the present implications to cosmology? It's not as simple as altering some lambda CDM parameters, because if these lambda CDM parameters are consistent with the HST measured UV luminosity function at lower redshift. So just tweaking those parameters will not work. So now at the moment, purely astrophysical solutions, which means modifying galaxy formation models rather than the cosmology, seems to be the preferred solution. We are fortunate that the earlier abundance claims, like very large number of excess of galaxies, was overestimated. That has eased the tension, and lambda CDM may still be fine. JWST early galaxies may tighten constraints on reionization and dark matter. So this has implications to some of the theoretical work that's going on, and whether star formation can reionize early or limited small scale dark matter structures, those will be affected. So people working on H1, complementary H1 observations and studies, theoretical modeling, will need to take these JWST observations into account. There's lots of future surveys coming up, lots of data. At the moment we have 25 galaxies with confirmed spectroscopic redshift greater than 10, all except one JWST discovered. That number will grow by an order of magnitude in a few years, couple of years. There's going to be lots of spectroscopic follow-up, and there's lots of beautiful synergies with ALMA and eventually with Roman and Euclid. And of course, as far as theory is concerned, we'll need improved simulations, better models to incorporate early star formation, the burstiness, the feedback and dust gas physics in order to correctly match the JWST data. I'll stop here and I'll leave you with my conclusions.
Yeah, we have a few minutes for questions.
Thank you for very nice overview, Yogesh. So I have a question related to outflows. Do you see any signatures of outflows in these high redshift galaxies?
There have been a few observations of outflows. Are you talking about AGN driven outflows?
Yes.
Or?
I mean, the next question was related to AGN. Do you see the AGN in the...
So there have been a few observations of AGN driven outflows at high redshift, say greater than 6. But remember, getting a IFU spectrum is fairly expensive. So we have lots of photometric data on JWST galaxies numbering in the millions. But the number of spectroscopic observations are still in the thousands or tens of thousands. So I think it should be doable, even with, there's lots of, forgot to mention that about 50,000 reduced spectra are publicly available now. And so people can create their own subsamples of, let's say, AGN and see if you can see outflows in those. Not all of them are MS, the multi-shutter array spectra. So you won't get IFU data, which is what you really need. Also, the resolution may be a problem. So if the outflows are happening on lens scales which are too small for JWST to probe, you won't see it.
Yeah, and when you say spectroscopic redshift confirmation, which resolution you use in NearSpec, for example?
It's mostly for the most distant galaxies, people operate in prism mode, which is that 100. Okay. And that is enough for you to see the Lyman break clearly.
Yeah, but if you observe with the 3000 or 2700, you will not see any difference in the spectrum.
Very faint.
Very faint.
I mean,
okay.
even with JWST, it's very faint.
Right.
Yeah.
Thank you.
Yeah.
There was one somewhere.
Hi Yogesh, thanks for the nice talk. I'm curious about what are the prospects of getting the dark matter masses or the dynamical masses for some of these galaxies. I know for GN-Z11 people have got at least some points of the circular velocity.
Yes.
And that's at redshift whatever, 10, 11, whatever.
Yes.
But what about...
So I think we can now do it between redshifts 8 and 12 or 8 and 11. There we have sufficient numbers and the galaxies are sufficiently bright for effective, significant signal to noise measurements. And I believe people are trying to do that already.
What instruments are they using?
JWST NIRSPEC, yeah. There's nothing else actually, because like even at redshift 5, 6 and so on, with HST you see nothing, right? And, even with WIFC 3 is not very sensitive. HST ACS, which operates in the optical band, is sensitive, but once your UV just flows across it, you don't see the galaxy at all. Even Alaknanda, which he showed, is only visible in JWST. It's not visible in HST.
So you showed in the beginning one galaxy at redshift 3 or so.
Yes.
So it looked like a face-on galaxy.
Yes.
So how do you get the rotational velocity of this one?
It's not fully face-on. It's inclined at some 20-30 degrees or so. So you can therefore get significant, and it's rotating. The sort of inclination corrected speeds are 200 kilometers per second. So it is rotating like the Milky Way, but it is sufficiently inclined for you to get a reasonable measurement. You can assume a disk, and the disk is circular, so you measure the ellipticity of the galaxy, and as it becomes more and more tilted, you can get inclination.
Okay, I had a quick question about, you said we don't have to worry about the basic lambda CDM model right now with whatever astrophysics. So, but lambda CDM, there are two parts to it. One is the background model and the perturbed thing. Do we have the seeding mechanism is this Gaussian random field, right?
Yes.
Is that good enough, or is there something new that can be added there? Like, some things like many of people are talking about in terms of seeds for, dense.
So I think it's a bit premature, in the sense that it is actually a bit premature for observers to make any strong claims. Because there are, I have shown you the sort of just the top high level picture, or everything looks good kind of thing. But there are some worrying details in the observation which need to be figured out. So I think it's totally premature for when observers themselves are not trusting their observations fully. It's a bit premature for theorists to start working on the basis that the observations are very good. So they're very sensitive, but that doesn't mean that the numbers they're giving you are correct. So there's a difference between precision and accuracy.
Good to hear this.
So there's a difference between precision and accuracy. The numbers are very precise, but doesn't mean they're accurate.
Okay.
Last question and then
So the list of issues that you listed at some point in your slides were all too much, the number counts were too much.
Yes.
So does that indicate something about the nature of how inference is being done?
What do you mean by that exactly?
What I mean is there is nothing which is lower than expected, right? Everything is above the numbers that are expected.
Yes.
So that would mean that maybe some way of counting cutoff is too.
There could be, but people have tried to see what's happening. There is one trivial thing which some of the earlier papers didn't look at, which is there were predictions of how many galaxies it will see per square arc minute, okay? But these were based on the nominal sensitivities of JWST. So on one of my latest slides, I think this is a very trivial thing. JWST turned out to be 20% more sensitive than what people was the design value. So you just found more and more fainter galaxies, and you also said there are more galaxies than we expected. That's not correct, because people were comparing the theoretical numbers. So there are many factors that have to be taken into account. But certainly one thing is true, one is going towards more galaxies at high mass, more galaxies at low mass, more AGN, more rapid growth of black holes, more rapid star formation. There's nothing which is less.
Thank you.
I'm going to be around till tomorrow lunchtime, so if people want to chat to me, I'm there.
Next we have Kannan, who is going to be telling us about probing cosmic dawn and reionization with SKA.
Hello, I am Kanon Kumar Dotto from Jadavpur University, Kolkata. The title of my talk is Probing Epoch of Reionization and Cosmic Dawn using Square Kilometer Array. This is a broad title. The things that I am going to focus on are there are mainly two aspects that I am going to focus on. First is modeling the H1 bispectrum during cosmic dawn, and the second one is prospect of detecting individual ionized bubbles in 21 centimeter map using SKA. And this presentation is based on these two recent work. So here are some basics. So the measurable quantity in 21 centimeter cosmology is the differential brightness temperature, and then exact expression for the differential brightness temperature is as follows. So it is basically the difference between the spin temperature and the CMB temperature, which the H1 21 centimeter optical depth, which can be written as follows. So as we see that H1 21 centimeter optical is proportional to the spin temperature, and it is proportional to the neutral hydrogen density. Now in most cases this optical depth is very small because spin temperature is very high. So one can assume e to the power minus tau as 1 minus tau, and then this expression can be simplified as this, and if we put the expression for tau here, we will get the differential brightness temperature as this, and this is the equation which is widely used to calculate differential brightness temperature, but this assumption goes in there. Now we will actually look at this assumption carefully during the cosmic dawn. So here this plot on the left shows the mean spin temperature as a function of redshift, and for two different models. So initially spin temperature is coupled with the background kinetic temperature of intergalactic medium, and it decreases with decreasing redshift. That's because universe was expanding adiabatically during that time. Now so and that scaling is 1 plus z square. Now at some point X-ray sources started to form, and then X-ray photons started to heat up the intergalactic medium. So that's why the spin temperature rises as we go from redshift around 15 to 10. So so of course this is from this model, but this is a generic picture that spin temperature will be minimum at some point. Now as I showed that optical depth is inversely proportional to the spin temperature, that means at this point of time is your spin temperature, your optical depth is reasonably large. Not only that, so this is a mean behavior. If we look at the fluctuations in the spin temperature, we see that there are places where spin temperature is actually very low, can be 4-5 Kelvin, and then you have considerably large optical depth. So here I show the distribution of H1 optical depth from our simulation, and we see that although the mean optical depth is around 0.1 at redshift around 13-14, but it has a long tail and it can go up to 0.5. So that means that approximation may not valid anymore. So if we calculate the mean differential brightness temperature as a function of redshift, here are some results. We see that if we calculate it accurately, then the global 21 centimeter signal, the global differential brightness temperature gets suppressed by up to 10%. So so it's a 10% effect in global 21 centimeter signal. However, if we look at the non-Gaussian signal, the effect is quite dramatic. So the figure on the left, it shows probability distribution function of delta TB from our simulation, and we see that signal is highly non-Gaussian. It has long negative tail, this blue line. However, if we calculate the delta TB using exact equation, this long tail gets suppressed. So that means the non-Gaussianity gets suppressed. So we calculate bispectrum for equilateral triangle configuration and squeeze triangle configuration using our simulated data, and we see that the bispectrum is actually quite different. This is in log scale, so we don't see it, but if we calculate the percentage difference between two different approximate method and accurate method, we see that the changes in the bispectrum can be anything between 10% to 300% if we plot it in terms of redshift. So it's a very significant impact if you want to model the bispectrum during cosmic dawn. Okay. Then the second aspect that I want to study is that detecting individual ionized bubbles via match filtering using H121 centimeter data with the square kilometer array. So before I go into the actual topic, let me briefly tell about the square kilometer array. So it's an international project to build world most sensitive telescope with a collecting area of 1 square kilometer, and it consists of two components. One is a scale low, which operates at low frequency between 50 megahertz to 350 megahertz, and it is being built in Australia. And then second component is SKA mid, which will operate at 350 megahertz to 15 gigahertz, and it is being built in South Africa. There are several science working goals, but the ones that I have listed here may be interesting for the community here. So it will probe cosmic reionization and cosmic dawn. Particularly, it will try to answer these questions like timing of the epoch of reionization, properties of fast star galaxies, and it will also probe thermal and ionization history of our universe during the epoch of reionization. And also it will provide key information regarding dark matter, dark energy, modified gravity, and all other things that we have discussed in this meeting several times. Okay, so now so this full square kilometer array, so it will be built in phases, and it is expected that currently given the funding available, a sub version of square kilometer array will be built. So it will have like 0.4 square kilometer collecting area, and name is A star. So it will have 307 stations. It's like a 307 antenna, and the timeline is that beginning of 2028 it will be completed, and actually observation will start in the beginning of 2029. Now this here is the antenna distribution. Out of 307 stations, a large fraction will be placed in a very small region, and that will give you excellent sensitivity at large angular scale, which is very important for UR and UR study. And it will also give you 3-degree field of view at 150 megahertz, and so it has maximum baseline 73.4 kilometer, which will give you 6 arc second of spatial resolution at 150 megahertz. And one of the most important point for SKA is it's a highly sensitive instrument. So here I plot a sensitivity parameter as a function of frequency, and we see this blue line shows the sensitivity parameter for the SKA low and SKA mid, and you see it is at least 5 to 10 times more sensitive than current available telescopes. So with this advantage, we study the questions like whether we can detect individual ionized bubbles around bright luminous sources. So in the last talk, Yogesh already mentioned that there are many very bright galaxies and quasars detected by JWST. So for example, 2011, this paper reported discovery of a very bright quasar at redshift 7.5, and 2024 there is also detection of a bright galaxy cluster at redshift 8.3, and there are many more that you have already heard from Yogesh talk. So UV radiation from those sources will create ionized bubbles around it. So it's a cartoon picture, and that ionized bubble will be buried in neutral hydrogen medium. So that is the kind of objects we want to detect. So we want to study the prospect with the square kilometer array, whether it can detect and how many hours of observation it will require, and whether we can measure the bubble size and constant the neutral hydrogen fraction outside it. So these are the questions we have studied. Now if we consider perfectly spherical bubble sitting at some point inside a uniform neutral hydrogen medium, we expect visibility, that is the observable quantity from interferometric array. So the visibility will look like this red curve, that is the ideal situation, and if we plot the visibility as a function of frequency, it will look like this red dashed line. However, in reality, the bubble is not, spherical at all. So it will be aspherical, and there will be many other bubbles which will be overlapped with each other. So, so we still want to study the prospect of detecting those sources, because so far the UR detection strategy has been on statistical detection. So we want to ask whether we can still detect individual ionized bubbles, and that will be very important because we can directly interpret these objects. It's a very straightforward interpretation. So, so now this H1 signal is extremely weak, as you know, but this signal will be overwhelmed by the foreground sources. So one of the most important foreground sources is the diffuse galactic synchrotron. So it is a synchrotron emission emitting from our own galaxy. So we simulate that radiation using this kind of angular power spectrum model, and so you see this temperature, it is 60 Kelvin plus minus, and if you compare with the H1 signal, it is only a few millikelvin. So it's already 100 times, more than 100 times stronger in image. In power spectrum, it is 10 to the 4 times stronger. So it's very strong foreground signal. Not only that, we also have radio emission from extragalactic sources. So we also simulate those sources using this DNDS model. So now we have this total signal, that H1 signal, and also two components, foreground signal like galactic diffuse synchrotron radiation, and also point source contribution. So we add them all together, and then we convert them into visibility, simulated visibility. Then we add system noise based on SKA observations. So this is one example, SKA baseline distribution. So we simulate visibility at these points after adding all those components. So now we have mock simulation data. So now this mock simulation data will be overwhelmed by the foreground components. So we need to first subtract out the foregrounds. Now one of the ways we can subtract the foreground is that foreground is assumed to be spectrally smooth, and H1 signal and noise is not spectrally smooth. So we use that property and actually apply polynomial fitting along each baseline along frequency axis, and we subtract out the smooth component. So what is left is given here. So this blue line is the original signal plus noise. So the residual signal will be composed of signal plus noise, and this dashed line is what we have recovered after polynomial fitting. Of course, this is a very simple polynomial fitting. In practice, it will be much more complicated, but in this simplified picture, we can recover this signal. So now we have residual signal because we have subtracted out the foreground part. So this residual signal is still dominated by noise. It is a very strong noise. So now what we do that? So we use the mass filtering technique. So we know that there is a bubble in the signal, and we know the functional form of it. So basically what we do, we apply match filter, and then we multiply the match filter with the residual visibility, and we take sum over all baseline and frequency channels. So that is our estimator, and this is the variance of the estimator. So we calculate it, and this is the signal to noise ratio, this estimator by square root of the variance. So this is a very simple picture of the match filtering technique. So we apply this technique on our residual data. So these are the results. So this is x-axis shows the filter size, and y-axis shows the signal to noise ratio. Basically, we know the so we assume that we know the source location. So that's why, but we do not know the exact size of the ionized region. So we try with different filter corresponding to different filter bubble size. Now you see that the SNR rises and then it peaks at some filter size, and it then again goes down. That means that, so according to match filtering technique, we know that when the filter and bubble hidden bubble size matches with each other exactly, we get a maximum signal to noise ratio. And these are the different curves. It shows results for different independent realizations. So we have 100 independent noise realization, and we add them with the H1 signal, and we study the match filtering technique for all cases, and we see in each cases we can recover the bubble size and also the SNR comes out to be around 6. So that depends on the, of course, observation time. So so now we study how reliably you can extract the bubble size. So we have drawn the histogram of extracted bubble size for 100 realization, and we see that we can almost reliably detect the ionized bubble size, right? So now we have carried out these 3 studies and corresponds to these quasars and galaxy clusters. So this bubble size, input bubble size is here, and these are the extracted bubble size. Of course, we do not know the bubble size, so but this is there in the simulation, and it can reliably extract that. Not only that, it can also extract the neutral fraction outside it. So this, so in our simulation we have a neutral fraction of 0.52, and the extracted neutral fraction is 5.37 plus minus 0.056. So you can see that we can actually reliably detect, measure all these quantities, right? Now, so we also have carried out MCMC analysis, because so now we have 5 parameters, like we have ionized bubble size, we have neutral fraction. We also do not know the exact, if we do not know the exact location of the bubble, so then you have these 3 parameters, theta x, theta y, and delta nu, and we have done MCMC analysis and tried to extract those parameters, and we can see we can reliably actually extract all these parameters for a typical observations of SKA A star to 200 hours observations at redshift 8.3. So yes, so now we have developed a pipeline that actually can reliably measure all these quantities. Now this is a more complicated. So this is again MCMC analysis, but for more complicated scenario where you have spherical ionized bubbles, and there are other ionized bubbles around it. Whether we have asked the question whether still we can recover the bubble parameters, and yes, so we can still recover bubble parameters like bubble size, neutral fraction, and its location, but their uncertainty is more. So maybe we need to observe more, or so yeah. So this is our results, and this is a plot of signal to noise ratio only for 20 hours of SK observations. So this SNR can be enhanced if we observe more and more. Okay, so I'm done. So now these are the conclusions. So I have basically studied 2 main aspects. One is that if we want to model bispectrum during cosmic dawn, the assumption that optical depth is much smaller may not be valid anymore. So we have to consider the full exact equation to model it, otherwise bispectrum will be highly biased. Then second topic that we have studied is whether we can study whether you can detect individual ionized bubbles. So far the aim target was to detect signal statistically, but we have asked whether we can still detect individual ionized bubbles, and we have developed a match filter based technique. We have verified our technique using mock simulation, and so far the results are very promising. So thank you for your attention.
Thank you, Kannan. So I have a rather very naive question. You mentioned that in your match filtering technique, noise is important, very important, but you also make an assumption that it is a Gaussian random noise. So
Yes.
from SK like observation, do you expect the noise to be Gaussian random, or it could be correlated? That might reduce your constraints on the bubble
Yeah,
sizes.
I think that's a good question. So we have in our simulation we have added only Gaussian noise. Now if it is not, then we haven't investigated that. So maybe we can try correlated noise, time correlated noise. It will still work. Yeah.
Thank you.
Yeah.
Yeah. Can I?
Yeah, go ahead.
Yes.
So this is regarding the bubble size estimation. So what I remember is that at ionization fraction half, the ionized regions are not exactly localized, but many mergers have happened, and they are highly, the shape is very irregular.
Yes.
So how exactly are you determining a bubble size from that?
So, let me show the picture here, one such example. So, picture will be something like this, right. So, you have this quasar bubble, but there are other bubbles merged together. So, match filter will try to maximize the signal to noise ratio. So, it will give you some characteristic size. So, radius can be defined for sphere only, right, but for irregular object you cannot define radius, but it will try to measure radius which will, so the filter will try to match with the signal. So, it will be some characteristic bubble size it will provide.
So it will ignore the merger information?
No, it will not completely ignore, it will try to match. So, it will make the size little bit bigger and try to incorporate some part of it.
Okay, maybe it will work better at slightly higher redshift.
Yeah. So, for example, redshift 14, it will be isolated. So, it will work excellent for isolated sources, but it will also work for merging sources also.
Okay, thanks.
Yeah. Yes. Yeah.
Matching one size over there.
No, so for this, let's say for this case, it will try to, so yeah, so it will, so let's say you have this large ionized region here, it will large ionized region here, so it will not consider that in match filter. It will try to, if you look at this ionized bubble here, so you see this part is spherical, but that part is not. So it will try to match with this part.
Right, but if you go to the left of that, there are, I can think of two other spherical sizes which will be smaller size. Now in match filter, you change your size.
So I can change the center of the filter. So I can scan through the image. So it will
okay, at one XY and then a size.
Yeah.
No, I don't know whether it is reasonable question or not, because see, instead of doing one, I know that your aim is to get one. But if in the field there are several candidates,
yes,
quasar is one particular time where this is flaring up. Otherwise, the nearby guy would have gone like this and created these bubbles, right? So can one think of stacking so that you will get an effective bubble size, right? Because that will be more or less spherical. So is that possible, or is this unreasonable thing?
See, you are without match filtering.
Of stacking and then trying to locate the sizes, average size.
That can also be done, and in that way, actually, you can also enhance your SNR.
Because it will be spherical most of the time, because you are adding.
Yeah. So there
you can keep on rotating and adding.
So there are papers on that.
Okay.
So there are papers on that. So we are studying the same thing that you have here. Yeah.
I'm a bit late.
Yeah. So one of your contour plots, there are multimodal distributions, right? Is there any reason to expect multimodal distribution?
This one?
Yeah, this one, yes.
No, so this is because there are so it is trying to match, and so it is scanning. So for example, if you look at this panel, so you have this theta x from minus 80 arc minute to plus 80 arc minute. So it is scanning through the image from minus 80 to plus 80, and there are multiple small ionized bubbles. So it is actually picking up. So let's, for example, maybe there is a bubble here. So it is actually detecting those as well.
What especially about delta nu that has more?
So it is there along the frequency.
Along the lines.
Yeah.
Okay, thanks.
Okay, I think we should move on. So let's thank the speaker again.
Yeah, thank you.
So next we have Saptarshi, who is going to be telling us about ANN based emulators.
Am I audible? Okay. So hi all, I am Saptarshi from NCRA. Today I will be presenting my work that I have been doing with Teeth. It's about using ANNs for accelerating parameter inference. Before we go to ANNs, I would like to discuss about parameter inference so that we are all on the same ground. So to describe it in a few words, whenever you have an observed data X and you have a model that predicts this observable, that is parameterized by some parameters theta, and you want to know what are the model parameters that are allowed by your observed data. And typically you will have some errors in your observed data which will lead to a range in your allowed values for theta. Now typically we use a Bayesian framework to do this thing, where the whole game now becomes one of calculating the posterior given the likelihood and the prior, and most of the times the evidence is not known because it can be computationally expensive, especially for simulations. So in those cases, instead of computing this analytically, we go to MCMC, where it becomes a iterative thing where you sample from the prior, you run a simulation, you calculate the likelihood by comparing with the observed data, and you have some acceptance criteria based on which you accept this sample or not, and then you create a chain of samples that as it converges becomes statistically equal to your posterior. But now there are a few problems with this conventional MCMC based approach. The two of them are, first, it is very inefficient, especially when your number of parameters in your model becomes very high. The number of simulation runs you need to do for the MCMC to converge goes exponentially. Secondly, when your individual likelihood computations are very expensive, then also this becomes very, this MCMC becomes very expensive to run, and when these two issues are combined, MCMC becomes unfeasible to do. So a possible way out to solve these issues has come up in recent years is to use emulators. What emulators are basically you run your model at a predetermined set of points and you train an emulator which will then interpolate the model output at other parameter points in a very fast and accurate way. But for reanimation studies, because you have high dimensions, you can't use normal emulators, you need to go to machine learning based emulators, and these have been shown to give very fast and accurate interpolation results, and these are been widely used in reanimation studies on all these papers. Specifically in 2023-2024 there were two papers from our group which showed that you can use GPR based likelihood emulators. Typically we have not used likelihood emulators before. In all these papers they typically directly emulate the observables, but we have shown that if you use likelihood emulators you can improve parameter inference and you can reduce the number of simulation runs required by up to 30 times. But we also know that ANN based emulators or artificial neural network based emulators can be much faster in both training and prediction compared to GPR and other ML based methods. So our goal in this work was to extend the work that was done previously using GPR to ANNs. So to do this we use a test bench where our model is script, the semi-integral code for reanimation with photo conservation, which is a reanimation code that gives us the reanimation state and the thermal state of the IgM at a given redshift. We use a box size of 256 comoving inverse megaparsec, H inverse, and we run the simulations at two different resolutions of 32 grid cells and 32 cube grid cells and 64 cube grid cells, and our model is parameterized by 5 parameters, and we use these observational constraints which are the CMB optical depth, the lower limits on Eisenhower fraction, the galaxy UV lift data, the low density IgM temperature estimates, and also we put a constraint that reanimation must end by redshift 5. So our approach in this work is to, so this was your typical MCMC flow chart. So what we did was we replaced this part by an emulator. So you do not need to run the simulation at each time, but you can just call the emulator, it gives you the likelihood directly and you can accept it or reject it as you please. So first we have in the literature, most of the emulators were trained using Latin hypergroup samples. So we followed suit, and we chose 10 to the 4 random parameter sets using Latin hypergroup sampling from within our prior range, which is 10 times lesser than what was actually needed to do a full MCMC. For these 10 to the 4 random parameter sets, we ran simulations at the required resolutions and calculated the chi-square values. We split them into trained test sets as is standardly done for training emulators, and we trained ANNs with varying hyperparameters. So when I say hyperparameters, I mean the neural network's length, the number of neurons in each layer, the learning rates, etc. And after this is done, we select the ANN that has the best test R2 score and use this to now do an MCMC by putting it here. So using Latin hypergroup samples, the results are this. They are not very good. So the blue one is what we are actually trying to replicate, and the green is what we get. So then we tried to artificially reduce the prior and sample with the prior reduced, but even then it starts to go near what we actually want, but it never really reaches there. And the reason this does not work is pretty apparent if you actually look at what is happening. So this is a slice from our parameter space. This is a full prior, and these are the blue points are the Latin hypergroup samples that we took, and the red part is where we actually want them. These are my high likelihood regions, and this is my actual posterior data I'm trying to replicate. So even if we take 10 to the 4 samples here, the number of samples in this region is very sparse. So emulator will never be able to learn very well what is happening in this region. So what we actually need is a number of samples much larger in this region, and we do not actually need these samples. So what we do here instead is we use script's convergence with respect to resolution, which means that in script, for a given set of parameters, even if you change the resolution, the output does not vary. So using that, we use a solution where we run a very coarse resolution MCMC, which is very inexpensive. We use a 4-cube MCMC, and using this MCMC chain, we take random samples from this, run high resolution simulations, and then use that to use our training data. So this is our new training strategy. So we run a very low resolution MCMC using inexpensive co-resolution simulations. We randomly select a small number of parameter sets, but now the problem is that we do not know how many training sets we actually need for the ANN to converge. So what we do is we run the simulation required high resolution 32 cube and 64 cube, compute the chi-square values, and then we, as was done before for the Latin hypergroup case, we standardize the data, we split it as required, we train the ANNs with very high parameters. But now once ANN is trained, we use it to predict the chi-square values for a given validation set that was not seen during training. And then once this is done, we train a neural network with more data and do a prediction again and see when these two predictions, we are computing the relative entropy between these two predictions, we see when this relative entropy drops below a certain threshold that we have defined. When that is done, we say that this ANN has been trained, and then we can use it to do our MCMC as we want it to. So this is the result using for the 32 cube case. We see that the red one is the full MCMC, and the blue one is the ANN based MCMC, and they are so on top of each other that you cannot even differentiate them. And you can see the full MCMC takes around 400 hours, while the ANN based takes 100 hours. This is not that great, but we will see. And the simulation runs have gone down, number of simulation runs have now gone down 2 orders of magnitude. The good thing about using ANNs is that the time that it took in the 100 hours, most of it was used to train the ANNs. So if you use a very high resolution, if you go higher resolution, this factor will be much better. So to check that, we use the same formalism. We do it for the 32 64Q case, and see what we see is that the full MCMC took 8,000 hours, yeah, but our emulator based MCMC just took 150 hours. And this remains constant because number of parameters in our model is the same, so the number of simulation runs remains constant. And again we see that the results are very good, they match almost exactly. But now we have gone from 1 year in computation time to just under a week. To summarize, using MCMC based inference, we have shown that MCMC based parameter inference becomes unfeasible when your models are likelihood computations are high or your number of parameters are very large. We have shown that we can use faster, more efficient parameter inference techniques are needed for leveraging upcoming high-redshift observations. And we have shown that ANA based likelihood emulators, when taking advantage of the model's convergence with respect to resolution, can dramatically accelerate the parameter inference speeds. Thank you.
So thank you for nice talk. I'm just slightly confused. Do you use this emulator on the fields or is it on the statistics?
So we use these on these observational constraints, not on the fields.
Okay.
On the chi-square, yes.
Likely. Okay. Yeah, but there are some papers which says that chi-square, emulation on chi-square might be wrong compared to the field, and then computing the statistics. So, no, I mean here it's okay, but there are some Liouvin alpha forest papers where it's not correct. So that's why.
In this case,
yeah, but
we
have
had
you
the
checked?
full MCMC.
Have you checked with the fields?
Yeah, I'll check.
You have checked.
No, I have not checked. I will
okay,
check.
Okay, fine.
Maybe I've asked you this before, but I don't remember. How many parameters do you have? 5
parameters.
Then it's a little surprising why you need so many simulations. So for example, you know, I'm coming at it from cosmological emulators. With 7 cosmological parameters, we needed 35 simulations. The Quixote Latin hypercube, again with 8 or 9 cosmological parameters, has 1,000 simulations. Do you know why you need so many more simulations in your case?
I'm not sure. Maybe it's because the priors in our case are very wide. Okay. But this is just what, so we use R-1 criteria in our, so R-1 is the Gelman-Rubin statistic that must go below 0.01. And that is what gives us this number of simulations as 10 to the power 5.
We can maybe discuss this. I'm a little surprised. No, that is okay, but how many simulations do I need to run to train my emulator? Yeah, so that number I couldn't see on the slide.
So that is
okay, then it's fine. Okay.
Yeah. So can I ask? Yeah. So have you tried using variational inference or normalizing flows? I mean, so my CS colleague Srijit has written a paper 3 or 4 years ago which showed that variational inference is much faster than MCMC. Or is there any reason why variational inference doesn't work for solving this?
So this work was basically done to extend previous work using GPR to ANNs, but we have looked into normalizing flows and we wish to work in it in our next projects.
Okay, what about variational inference?
No, that I have not checked it, I'll check.
Okay.
So just a nice question. So when you obtain your training sample based on coarse grain MCMC, and then do the inference later based on that, is it similar to double counting of the information in any way?
Can you repeat?
So when you train your sample, like obtain the training sample using coarse grain MCMC, and then do the inference based on that training sample, the emulators obtained from that training sample, is it like using the same information twice in any way?
No, it is not, because the initial MCMC that we do is a very low resolution one.
Yeah.
And for the training, we use the same initial MCMCs, only the parameter points, and then run a new high resolution simulation that contains the high resolution information.
Okay.
So that is our training data, not the initial MCMC itself.
Okay. Thanks.
Okay, let's move on. So next we have Prabhabati, morphological complexity.
Okay. Thanks Dheeraj and all the local organizing committee for this wonderful meeting. I want to start by saying that I am going to talk about something I know very little about. It's baby steps for me, just because the images are too beautiful to resist. Okay, so I am going to talk about morphological complexity. So morphology, the word morphology is used in various contexts to mean various things. So here I am going to talk about basically the shape of galaxies, not exactly quantifying, but quantifying like in geometrical sense, but in the sense of measuring a statistical quantity called complexity. So this is a pilot study which I would like to in the future expand to many galaxies, and hopefully it will lead to a scheme for classification of galaxies. So this is the first step. And this work is done with Langlen, who is a postdoc in South Korea, EPCTP, and Amruta, who is a student in IIA. She is a student of my colleague Moushmi Das, but she is also my student. So, and Langlen was my intern student a few years ago, and Changbom Park from KIAS. Okay, so let me explain the context. So, all the statistical things, objects that we see in the world around us, they have order as well as disorder, some element of order and disorder. So, the subject of complexity basically tries to study or quantify these concepts. And so what I am going to talk about is, so when we say order, for example, I have put 3 examples here, starting from the extreme case of having a crystal which is perfectly ordered, all the way to an ideal gas which is completely disordered. Okay. So it has all these, there are many possible ways in which the individual elements of the object can be arranged. So that that number of ways will quantify the disorder there, and we have objects in between like us, or any of the material around us, and to on the large scales maybe galaxies. Since my talk is about galaxy, one particular galaxy, this is an example which has order plus disorder. So if we intuitively we think of a crystal as simple, because it is, intuitively we know it is simple, right? We know how it is arranged and so on, and it has one state. All the individual components are arranged in a particular order. And also when we have an ideal gas, we know how to set up the equation thermodynamically or statistically. We know how to set up the equations. We understand the system, and so we associate the word simple to it. Then anything else that lies in between is here, they are complex, and it will be nice if we can quantify the level of order, disorder and complexity. So this is the context, and in order to do that, to quantify, so this plot here is just to tell, on the x-axis is like the different kinds of objects. What I mean by parameter is that. And we imagine some, we can think of some quantity or quantifying entropy for the disorder, and some quantity called complexity, which will go from here to here. So how do we set up that? And so for this, I'm going to use a formalism which was basically initially set up by Louis Mancini and Calvet in statistical physics, and they developed some measure on which, so if I plot entropy here and I plot complexity here, I'll just define them in a moment, and then I can classify various objects in between, where will they lie. So, did I skip something? Okay. So, that the ideas were set up in that paper, but the calculational framework was developed later by in a series of papers. So, when we are dealing with data, then the idea set up by Louis Mancini and et al., that previous paper, that was a conceptual, how do you calculate states and so on, but it does not give the clear outline, algorithmic outline how to calculate. So, that kind of outline was developed by using something called the ordinal framework, and I will just explain very briefly what that does. So, our goal is to, given a system which is a data set, I want to have a way to define a state, and I want to have a way to count those states, and from that I will build all these other physical quantities that I am interested in. So, in 2 dimensions, because I am going to talk about galaxy, which I am going to assume to be a 2-dimensional object. So, we will have a matrix, for example, the intensity of the galaxy in different pixel locations will be numbers of this type, and so the way to calculate the states is to take, so here I am demonstrating with an example which is a 3×3 matrix. So, I can define a subset of this matrix. Let us say I take a 2×2 matrix, first 2×2 matrix and then next one, and then go down and so on. So, I will have out of these 4 matrices, and from here I look at the numbers values and organize them in ascending order, not in ascending order, sorry, in a particular sequence. Okay, first row and second row I organize. Then based on their I assign numbers, these are just placeholders 0, 1, 2, 3. Then I sort them in ascending order, and then how these numbers, the placeholders get permuted finally, that is what I call as a state. So, I will have 4 states here. Now, this is just a 3×3 matrix. In general, when I have a large matrix n cross m, so I will call this dx dy. Here I use 2 and 2, so 2×2, that is called the embedding dimension, and from based on that, given n, capital N and capital M, I can count how many possibilities are there and so on, and I can count, I can construct all these sets. So, the set of all these sets, states that I have constructed is called the ordinal set. It will be indexed by where I can have I and j index to do that, and out of all these possible states, only some of them will be distinct. So, this is in the case when I have a large number of states and distinct states are few. Okay. So, there will be few distinct states. So, for each distinct state now I can count in the ordinal set how many times each one occurs. So, this is going to be my basic quantities from which I can construct my observables. So, from here I can I construct something called the ordinal probability, which is the number of times each distinct state occurs given by the total number of states. So, this gives me a probability for the distinct states. Now, I have the basic quantities ready, and these are the people who developed this further for calculation. So, I am going to define an entropy from the probability that I just defined, ordinal probability, and then I have this is just a normalization factor. So, the quantity what I am going to call permutation entropy is this H, which is the normalized entropy. Then, so that is the first step, which will measure the disorder. Then this equilibrium is basically, so given the probability that I have just constructed, how far is it from equiprobable distribution, that I can measure that. That is in information theory there is something called the Jensen-Shannon divergence. So this is the telling what that quantity is. Okay, and it is again normalized by a normalization factor, which I don't show because it's long. So this quantity, now if I multiply the entropy to this, then this quantity is called the complexity. So I am interested in H, DE and C. Basically I will be more interested in H and C, and I am going to ask, can I classify galaxies by measuring this for each galaxy. Okay, so today I will have one test galaxy, and that is this is the NGC 628. This is an image from JWST, and you can see there is randomness and there is order, there are structures and so on. So my goal is to quantify, calculate those quantities that I defined for this particular galaxy. Okay, so the questions are, I have already explained the questions. This is a big goal, and this is the first step by using this galaxy. And what I am going to do is measure complexity at different length scales and across different wavelengths to see how does it behave. Okay, so regarding the data, so I am using archival data. So I chose this because I wanted to basically use UVIT data, and so also UVIT plus it should be available at many redshifts, sorry, not redshifts, many wavelengths, and so these are the four. So UV, NIR, MIR and millimeter from ALMA. These are the three data that we use, and these are the particulars about the resolution. So JWST has a smaller field of view, UVIT has very large, so everything is brought to the same resolution and same field of view, and roughly in the parsec size my resolution is going to be like 20 parsec. And I will play around with these three embedding dimensions, so I can 10. Okay. Okay, so so now let us look at the four images and in the four wavelengths. So in this is the UV image. So here I did not mention it here, but so this is smoothed with about 20 parsec resolution, all of this, so that they are all equivalent, and we are going to smooth it at different scales to see how does the properties change as a function of smoothing scale and across the wavelengths. So in this y axis and z axis is what we are interested. And just to have an idea, we plotted the intensity probability distributions of the intensities, and these are the kind of distributions we get. They are probably can be fit by log normal. Okay, so the one point to mention here is that clearly as we smooth to larger and larger scales, of course the small scale fluctuations are going to get washed out, and the images will go towards these well ordered kind of behavior. Okay, so it's good to take a look at the ordinal probability. So the ordinal probability I am showing here for the case of 2 cross 2, it will depend on what this is, and this circle, diamond and so on, they are representing different wavelengths. So so clearly you can see that they are differing from, I mean if I just focus this on the circle 1, so circle 1 is here 1, so they are clearly differing from equiprobable distribution, and the idea is to measure how far away from equiprobable distribution is it. Okay, so I start with the results. So first we measured is just to see how the entropy and the complexity behave. So as we increase the smoothing scale, these are in units, 1 means 2, the sigma is a smoothing scale, so 1 means 20, 30, 20, 40, 60 and so on, that is how it goes. And so you can see that the entropy decreases as you go to higher smoothing scale, this is expected, visually it is easy to see. Then the disequilibrium, whereas on the other hand the disequilibrium increases, and the complexity will be basically, C will be basically a multiplication of these two, and these are the kinds of behavior that we see. So now from here we cannot extract much physics. So to do that, let us look at, so my interest is in plotting the C versus H, using the C versus H as like a phase space place where I can say, okay, each galaxy will occupy one point. So here of course I am plotting, I have H on the x axis and complexity on the y axis, and here these arrows are indicating smoothing scales from smaller high resolution to low resolution. So you can see them behaving in this way, and these are the different embedding dimensions. So there is a dependence on the embedding dimension. So what stands out here is roughly these NUV, NIR and MIR, they have a sort of a similar behavior, whereas the millimeter shows a slightly different behavior, and we think that this is because the millimeter emissions are coming from CO j equal to 2 to 1 transitions, and they are cold and clumpy, and so they have a different behavior. So this is the one first thing, and then now I am interested in looking at across wavelengths. So I fix the smoothing scales, and then I look at, is there a systematic behavior, do they occupy behave nicely on the CH entropy complexity plane, and this is the what we have found. So let us examine little bit clearly. So at small scale you can see they are all very, they are distinct from each other, the points. So this is UV and it goes down to millimeter. So they are distinct. Now as I go to higher and higher smoothing scales, I find that they are now becoming, they are behaving in the same way and getting clumpy, and it is not, we are not able to distinguish any further. So now just by visual eye, I want to quote this number, a quantification is being done, but I can identify some rough scale, maybe 80 parsec from here, which sort of distinguishes the behavior of the galaxy at, which is sort of the same for the different, it's a scale at which all the images at different wavelengths, they have similar properties, and above that, below that they differ. So the relating to the physics of the galaxy, so we know that the galaxy has stars, it has stars, interstellar medium, there is dark matter, and there is gas and dust and so on. So what we think is happening here to interpret physically is that, so the random fluctuating nature of the distribution in stars and ISM, that makes a transition at this scale from the random nature to a self-organized behavior, and we think it is related to the size of OB associations. So if my knowledge is correct, OB associations, these are some kinds of stars, and they are clustered at some scale, and this I think we can relate this to the size of the way those stars are clustered. So what is happening is that the stars will give out UV light. The UV light will stir off the interstellar medium. The light will be absorbed by dust and so on and re-emitted in the other wavelengths. And so what the star produces is used to stir up and cause turbulence in the interstellar medium, and so there is a cascading effect, and that is what we are seeing here. Whereas it is very weak in the CO regions, which is what I showed you in the previous slide, CO regions, because they are already clumpy, they don't have much diffuse structure. Okay, so then finally my interest is in looking for universal properties. So this is a plot where I have plotted all the wavelengths and different smoothing scales together, and what is interesting, we were not expecting this, what is interesting is that they seem to all lie, there seem to be a trajectory, attractor trajectory here towards the smoothing scale, higher smoothing scales, there seems to exist such a trajectory where all these, for all the, which is specific to each embedding dimension, and they all get attracted towards that. So now this cyan colored line, this is what we did is we made Gaussian random simulations, white noise, and we smoothed to scales, different scales to find is there some, does that give us a standard trajectory towards which all the other galactic properties will converge. So this is actually a Gaussian simulation of the appropriate size suitable for the images that we took, and we find that it fits very well. What we found, and I am not showing here, is this is an isotropic Gaussian random field, and if I change the isotropy, if I introduce an isotropy, then these plots are differing, and so this particularly specific to this NGC 628, it seems to asymptote to this behavior. Okay, so I think I am close to the end. This is my summary. I have just studied the morphological complexity of this galaxy, NGC 628, and this is the first step towards classification of galaxies. I am hoping to apply this to a large set of galaxies and see if there is how they distribute, particularly in this plot. Where do they lie? Thank you.
Questions?
Yeah, hi,
Yeah, okay.
Prabha. So nice talk. I have a question about the second last slide that you have.
Yeah.
Like if you have, if
This
you look
one
at
or
the
previous?
same, the one previously. So, on this plane, have you tried to take images of different galaxies at in the same filter, say JWST or
We haven't done that.
UVIT?
Yeah.
Because if you take and say a very regular galaxy like an elliptical galaxy,
Yeah.
and compare that with say an irregular galaxy,
Yeah.
you should see very clear trends on this CH
Yeah.
plane.
Yeah, we hope to
If
do
you
that
if you
next.
do that,
Yeah,
then
yeah.
you'll be able to
Yes.
at
Thank
least confirm that what you're getting seems
Yeah.
reasonable.
Yeah.
One last question, if there is anything. Yeah.
Yeah.
How does the entropy you defined, differ from Shannon entropy or Renyi entropy? Very naive question. So,
I don't know how those are defined. I know how this is defined. I mean, I need to look how those
I mean,
states
just like
are.
what minus sigma p log b. Anybody else knows the?
I can tell you how the entropy is defined here. So the states are being, I think they would be related, because see the basic thing, definition of the entropy is not the main thing. Definition of entropy is here. It is, the formula is the same.
Formula
But-
looks the same.
Yeah, but the point is how do you construct the state and how do you count the state. So the state construction is here for me. This is a procedure in which I am doing so it looks at these permutation states, we call it permutation states. So look at neighboring neighbors, neighboring intensities, sort them out, assign a state to it, and find out all the distinct states and how many times each distinct state occurs. That is the way this is calculated. So I don't exactly know how to answer your question because I need to look up the literature and see how the state is defined.
Okay, I think we should move on. We're running late. So, thank you. So, last speaker, Sai, on cosmic web.
Hi, I'm Sai, and today I'll be talking about exploring filaments in the cosmic web. Yeah. So after the talks of the past 3 days, I don't think I need to motivate that we need to go to beyond 2-point statistics. But I'll try to briefly summarize the major points. So the late-time large-scale structure is highly non-Gaussian, and power spectrum is not enough to describe it completely. So to visually see this, this is the large-scale structure. Now we keep the same power spectrum, but scramble the phase so that all the phase space correlations are washed over, and this is what you get. So obviously there is more information in the large-scale structure than the power spectrum. Also, with the ongoing and upcoming surveys such as Euclid and DESI, there is going to be a lot of information on small scales, and we have to be able to extract as much information that we like from it. So people have talked about multiple things such as field level inference, more physically motivated statistics such as k nearest neighbor, Voronoi volume function, Mark correlation, and much more. What I'll talk about is getting information from the morphology of the cosmic web, wherein we look at the objects in the cosmic web and see what structure they have statistically. So what will this achieve? Approaching the same problem from multiple ways, you could get better constraint, you could possibly break the tensions in cosmology, and especially with the large scale structure, you could probe the nature of dark matter. So this image is similar to what the background of the poster of this conference looks like. So the cosmic web acts as a bridge between the very early universe and the late universe. Not only that, it lies somewhere in between the very large scales which you can describe using perturbation theory and the very small scales wherein you could apply virial theorem and things like that. And finally, it's a bridge between observations and theories, the very basic theories of the universe. What you see is this, but the model of the universe or nature of dark matter and nature of gravity will influence what the large scale structure looks like, and which in turn will affect the formation of galaxies and their evolution that we actually observe. So here is a movie of the evolution of the large scale structure, and you see that the skeleton of the cosmic web is placed in the very early universe, and as time progresses, what happens is the nonlinear regions become more and more nonlinear, and the cosmic web becomes more and more prominent. Yet the skeleton is laid out in the very early universe. So let's move to more literal bridges, which are filaments in the cosmic web. So broadly, the cosmic web is classified into 4 regions. There are large underdense regions known as voids. Around these voids are 2D structures known as sheets or walls. Where multiple such sheets meet, you have elongated regions known as the filaments, which are the most prominent features when you look at the cosmic web. And at the ends of these filaments are dense nodes. So filaments are these elongated structures which join the nodes. And this is a zoom in onto the last movie, but I have zoomed into a more dense region. And what you can see is that matter gets accreted onto these filaments and moves along these filaments onto the nodes. So these act like cosmic highways, and they have implications on galaxies and halos. So, okay, this looks pretty, but why do we study it? People are interested in multiple things. The cosmic web is, or filaments specifically, are very anisotropic. So they affect tidally the halos that form within them. People are interested in up to what order the halos are affected because of these filaments and how. People have also seen that because it accretes and feeds gas into the nodes, star formation rates are affected because of filaments. So are galaxy formation, evolution, morphology of galaxies, orientation of galaxies, and much more. Also, the missing baryon problem, wherein around 40% of the baryons today aren't observed. Those are supposed to be present in these filaments in the form of the warm hot intergalactic medium. So many observers are interested in filaments. Now more cosmology point of view, understanding the dynamics of filaments will provide insights into how the large scale structure formed and evolved. And also the nature of dark matter affects the large scale very strongly. For example, warm dark matter will wash over substructure in the filaments. So understanding them better will provide insight into the nature of dark matter as well. What I am interested in is looking at the dark matter filaments in phase space and to see if some kind of universality exists in them. So it's a well established fact that the dark matter halos follow this NFW profile, wherein more or less any halo you take in the simulation, it will be described broadly by only two parameters, mass and concentration. So here is one halo from a simulation and you see that the fit is really good. Note that this is not a stack, it's a single object in the simulation which can be fit by a function with just two parameters. So it is natural to ask that does such kind of universality exist in filaments in the simulations? And what do we expect? So broadly we'll expect filaments to be dense in the middle and they should go to the mean density of the universe, not as dense as halos because they are not completely virialized structures, but more or less such kind of profile. In terms of velocity, we also expect infall onto the filaments, and as we go along the filaments, we expect stuff to move towards the nodes. And when we look at the full phase space, we expect to see some kind of caustics there, which will provide us information about the boundary of the filament. Apart from just the fact that it is interesting to look at these profiles and do they obey universality, understanding them will provide insights into how the large scale structure formed and evolved to start with. Maybe if we could quantify the any filament profile by a few quantities, the distribution of those quantities might change as we change the cosmology or as we change the dark matter model. And using these, we could probably put constraints on cosmological parameters and almost surely put constraints on the dark matter models. So what do we need to calculate these profiles? Like in case of a halo, wherein you will need the center of the halo, in case of filaments, you will need the spine of the filament, which is analogous to the axis of a cylinder. So this here I have shown a density slice of n-body simulation, and I have applied disperse, which is a widely used filament finder, and this gives the filaments. They look pretty good. Why not just use them and go ahead? There are many issues. First of all, multiple filament finders exist in literature, each based on a different concept, and when applied to the same data, it gives you a different set of filaments. So for example, disperse, it uses Morse theory and persistence to find ridges in the density field of the density field. Nexus uses eigenvalues of Hessians of different quantities such as density or divergence of velocity, etc. And there are many more. The problem exists because there is no consensus on what defines a filament. Is it a ridge in the density field? Is it something related to the velocity Hessian? We do not know. But let's pretend for a while we know what it is. And we know, okay, this is the filament finder that has got the definition of filament right. Even then there are problems. So when you stick to a single filament finder, it is associated with multiple free parameters. And the way they are fixed is you apply the filament finder again and again with different parameters, look what the filaments look like, and the visually correct choice is the one you choose. So obviously this is not the most principled way to go ahead. And why the problem arises is that it's a chicken and egg problem. Unless you apply a filament finder, you do not get a filament. And unless you have a filament, you can't check how good your filament finder is. Right? Apart from this, there are complications arising because of substructure that is there in the filament as well. Now we try to solve some of these issues. So first of all, we solved the chicken and egg problem by creating mock filaments. So you could create multiple filaments, particle realizations of filaments, different kinds of curvatures, node masses, etc. Apply the filament finder again and again with different parameters. And now since you know the truth, you know how good the filament finder is. This will fix the parameters for you. Not only this, now that you know the truth, you can study biases in the profiles that you extract. And one of the major things we find is that curvature plays a very important role in the biases that you get in the invert profiles. And unless it's not good to stack all the filaments without considering the fact that there is curvature, otherwise you'll get very biased profiles. This is an example of a simple filament generated. And another problem is that once you say you have fixed all the filament parameters, filament finder parameters, still inherently there will be noise on the filament spine and you need to smooth it. And this noise varies as you change different kinds of filaments. And because of the inherent hierarchy in the filaments, these noise properties are different. So the usually used smoothing, which is known as nearest neighbor smoothing, does not work. So we solve this by introducing a new kind of smoothing, Fourier smoothing, which is basically you go to Fourier space, apply a low pass filter and come back. This is pretty much insensitive to the choice of parameter that you make, as well as a single parameter works more or less for all the filaments. Also, the parameter that you choose is more physically motivated because it's a length scale in the problem. We also add an optimization scheme wherein the parameter of smoothing can be fixed by looking at the density profiles. I don't have time to go into depth, but I'll talk over it. So you just focus on the left hand side plot. We have generated filaments of different properties, applied different kind of smoothings, and we look at the length of the obtained spine by the true length, its profile, its distribution. So what you expect is ideally a Dirac delta function centered on 1, and you see that combination of optimized smoothing along with Fourier smoothing technique gives you a pretty good result. Now we apply all these techniques to simulations and see what happens. Well, these are the density profiles and these are the velocity profiles, and I have taken the same simulation, the same redshift, and given different inputs to the filament finder like dark matter particle positions, density grid, halos, etc. And you see that there is no convergence, no agreement between anything, not just in the inner profiles but in the outer profiles as well. This is happening because you haven't, probably happening because you haven't taken into account the inherent hierarchy of the filaments, and using different inputs you are identifying different kinds of filaments and you cannot really compare across those. So we are developing a new filament finder based on Voronoi tessellation, which will take into account this inherent hierarchy of the cosmic web. So a tessellation is something that covers the whole volume by region such that there is no overlap, neither is there any gap. And Voronoi tessellation is created such that you have a set of tracers. It splits the whole space into cells such that every point in the cell is closest to this tracer as compared to any other tracer. This is not something new that we have come up with. It's been used in cosmology for decades. A more intuitive way of looking at the Voronoi tessellation is you sit on every tracer and start growing spheres. Every time 2 or more spheres intersect each other, you freeze that point so that you end up with the Voronoi tessellation. You see that these cells have information about the environment of the tracer used. For example, where there are a lot of tracers, the volumes are very small, and also they hold information about the anisotropy of the cells. For example, here you consider, say suppose I consider this to be a filament. In filament you consider it to be like beads on a string. The cells will be squished along the filament direction and not squished perpendicular to it. So we use this anisotropic information encoded by the shapes of the Voronoi cells to construct a filament finder. So here I have given a very rough dark matter density field through an n-body slice, And here you see the Voronoi tessellation, and it's obvious that these pancake-like squished cells can be joined together to form these filaments. To include the hierarchy, what we do is we progressively go down the halo mass. The most prominent filaments are supposed to be joined to the most massive halos, and the spine will also be constructed by comparatively massive halos. So we'll find these first, we will go down progressively and delete these filaments as we go down, so that you'll obtain the hierarchy of the filaments, and then you can look for universality in a more better way. So thank you for listening. I'll be happy to answer questions.
Question. Thank you for nice talk. How will you use the velocity information in this Voronoi kind of thing? Because it looks like only density field.
Yeah, so we were hoping to construct a filament finder which can be applied to observations, so no velocity fields. But then including it really helps. For example, I will ultimately want to define the full volume of the filament itself, and the velocity, the infall velocity gives you a parameter independent way of defining the radius. So we'll include it, but we'll construct it such that it can be applied to observations as well.
But you will use the same thing like Voronoi in
Yes.
velocity space?
No, we'll use density, Voronoi will be constructed only in density
Okay.
space, but we'll use velocity information to look at its extent.
Okay, great. Thank you.
Thanks a lot for this very nice talk. So maybe you already said this. So how do you decide the number of tracers as well as the distribution of the tracers?
So I haven't said this, and we are still thinking about it. First of all, the distribution will just put a cut on mass or any other quantity such as the V peak or something like that. And ideally we would like to construct it such that since we'll progressively go down this quantity, the threshold that we choose at each step shouldn't matter, so that finally we'll get a set of filaments which is independent of, not independent, least sensitive to the thresholds that we choose.
Thank you.
Thank you for the nice talk. So if you, do you care about the width of the filament, and if so, how would you find it in this sort of algorithm?
Yeah, so I do care about the width. So I'll first get the spine, I'll process it so that it's smooth enough, then I'll look at its radial profile, and when you look at it, you'll see that although these are not very trustworthy results, you will see a very strong dip in the infall velocity at the edge of the boundary of the filament. So you have the spine, I'll construct a cylinder, curved cylinder around it of this radius, so that I know what the whole object looks like.
About connecting the Voronoi regions, since you already have the Voronoi tessellation, you can just look at the Delaunay triangulations.
Yes.
Because then the Delaunay triangulations will actually give you the directions. The longer sides of the Delaunay will give you the filaments.
Yeah, so actually more than that, so that does help, but if you look at construct inertia tensor of the shape of the cells, it provides you way more information about the anisotropy itself.
Yeah, Delaunay will be the first guess, then you
exactly.
use,
Yeah, so right now we are using the tensor to start with. Yeah, so of course Delaunay will help, but then it will connect everything. So
yeah, then
it
you
will
have to
also
choose
connect
which ones
these
you
for
need,
that,
yeah.
So I have to put an anisotropy cut some point.